or others, operational manufacturers will be need to invest in both the hard infrastructure, but also the talent required operating, maintaining and updating the smart ecosystem. For smart system to be the truly effective, all vendors in the supply chain will be need to be the connected together and instrumental. We are the making the manufacturing optimization platform that helps you realize the promise of the smart manufacturing. I am very happy to inform that all of you know that because of all are the almost our corporate members, we are completed our 100 years, century years of the Institution of Engineers in the year September 2020, and we also celebrated this significant milestone with varied events in befitting manner to the glorious contribution to our national development. As a part of centenary celebration, the Telangana State Center, Institution of Engineers, and other centers also organized a series of international conferences and national conventions, all India seminars, workshops, and roundtable conferences in almost all engineering disciplines to disseminate the latest technology in engineering technology to our engineering community. The Telangana State Center has privilege to organize the prestigious 34th Indian Engineering Congress, which is apex activity of the institution, which is held 2019 at Hyderabad. It is very proud and privileged for the Telangana State Center IA that the Engineering Congress is organized first time after formation of Telangana State Center. I wish to inform that that IEA has been awarded, Telangana State awarded as the best state center for the best all-round performance of the 2019 and 20. This is a great achievement and honor bestowed on Telangana State Center out of 32 state center throughout the country. The Telangana State Center assured this honor for the second time, and keeping this spirit, Telangana State Center is positive of the developing an excellent center with all-round activities conducted in each and every sphere of the human activity as for spreading the technical knowledge and innovative technology for the benefit of our society and engineering community. I once again welcome to all of you, and today's event, eminent panel speakers and technical chairs. Today's our Satyanarayana Garu. I am very happy that HSCBIT now congratulating for initiating this type of events. And you know that our engineering staff college also we are doing a lot of programs this year also because of the pandemic. We are conducting all the online programs. So this year calendar also we are designed like that with different methodologies, training such as the training workshops, conferences, and best practice techniques, sharing of ideas, visits, and like that we are included. And the INSKE also we are also conducting PGDM program, sir, in our Engineering Staff College of India. This is a full-time 2 years program, JST approved. We are having this year PGDM Journal, PGDM Infrastructure, and PGDM Industrial Safety and Environment Management. Now admissions are open for the 2021. Sir. This is we are having a good faculty, and also placement is that almost 90% placements are there. But because of students are in the webinar, that's why for the to share these thoughts to students. We are also planning to set up an incubation center to make sure new technology to help promote the startups. So ISKE can take campaign to the new technology, both academic and industry. Such a campaign can be 3D printing, nanotechnology, IoT, software, safety engineering, environmental engineering, and energy efficiency technologies. I'm very happy to inform that the Engineering Staff College of India also offering third-party quality control and preparation of DPRs, electrical audit, energy audit, and water audit. And also we are planning new as a active partner in the new emerging ventures like Atmanirbhar Bharat, like that. So these few words, I once again extend my hearty welcome to the CBIT College for taking this type of initiatives. We will then together conduct many more programs for the benefit of the students. Wishing all the engineering students a bright future. Thank you for giving this opportunity as a part of the inaugural program. Thank you very much. Now, I am requesting Professor GPS Verma, Principal CBIT, please address the gathering, sir.
Good morning to all of you, and I welcome all the dignitaries from Institute of Engineers Chairman and past Chairman, and Institute of Engineers team, and the members from CBIT, and the guest speakers. I welcome you all to this workshop. And at this juncture, I'd like to share when this type of a smart or digital manufacturing system is a, a opportunity for every engineer to take up in the direction of manufacturing system in a different directions at this place. Being an Institute of Engineers, we as a part of that actually, and there are a lot of training programs are going on, a lot of skilling programs are going on, and we're all supportingly working out in this manufacturing system in this process. And this is the current scenario of the total world. In this scenario, all the manufacturing systems are changing towards mechatronics environment. In mechatronics, also in the smart systems environment at this place. In this connection, this topic plays a major role in this area. So I happen to be the one of the delegations taken place from Herman Bangalore Institute of Engineers to Israel. When we went there actually in Israel actually, and they the fantastic event has happened in 15 days actually. We went on a satellite mission out there, and I really appreciate the efforts made by the Institute of Engineers in that scenario. I mean, what the Israel people are doing, the technology in this direction, and it's inappreciable in this direction. The point here to mention that is actually here is when we went and we learned things out there, the technology involving in manufacturing system out there, technology involved in agriculture, technology involved in satellite manufacturing, satellite processing out there, nano satellites, all this was studied out there. In this connection, what I would like to mention is Israel's belief that actually the success is not important out there. They want actually whatever research they do, they want that to be failure. And first attempt, if it is success, it won't survive. What they say is it has to be failure. After several failures, the success comes. That is going to be a standard one actually. And that means what they want to say is if a failure is done actually, the failure study has to be analyzed. The failure study, after several failure studies, if the success comes, that is a robust model, and that is going to stand a long time in this process. So, in the COVID, in this scenario right now, the digitalization or smart manufacturing, or the mechatronics or robotics involved in the manufacturing in this process, all these things are emerging in different directions out here, and a lot of technology was involved in it, and also a lot of things to be still has to be added in this process. In this connection, my advice at this place is when you're working out, and please
Sir, I think network problem.
Sorry, traveling. Taking care of all the activities in the scenario. Yeah. So in this connection, I welcome all the delegates and the speakers and the Insta members and CBIT people at this place, making this event to happen at this place. I really congratulate all those people behind this event to make this event to happen at this place. Thank you very much for giving me this opportunity.
Thank you, sir. Thank you for the support that you have given to us. Thank you.
Thank you, sir. Now I am requesting our immediate past chairman, IEA Telangana State Center, Dr. S. Satyanarayan Garu. He is now chairing session. Now I am requesting, please start your session, sir. Can I introduce you, sir? Or no need to introduce you, sir, because of already know you about everybody.
రామేశ్వర గారు వారు హెచ్ఓడి కూడా ఉన్నారు చూడండి. హెచ్ఓడి అయిపోయిన తర్వాత రామేశ్వర గారి దగ్గరికి వెళ్తాయి.
Okay, sir. Oh, Ravindra Reddy, sir. Yes. Sorry, sir. Now I am requesting Dr. PVR Ravindra Reddy, sir, Professor HOD, Mechanical Engineering Department. Please address, sir.
Thank you, sir. Thanks.
Ravindra Reddy, sir, also our FI, sir. I am very happy.
I am MI, sir.
MI, no?
Yes,
okay,
sir.
Okay. Please convert your FI, sir.
Definitely, sir. I will upgrade.
Sir, you do some, now principal also very active. He is also showing interest. Sir, please conduct some of the programs in association with CBIT and our Telangana State Center, sir.
Definitely, sir.
Will involve.
It will be helpful to us also, sir.
Yes, sir. Yes, sir. Thank you, sir.
Thank you, sir. Thanks a lot. Respected Chairman of the session, Dr. S. Satyanarayan Garu, former Principal Director, CITD, Dr. G. Pradasarathi Verma Garu, Principal, CBIT, convener of the program, and one of the speakers of today's workshop, Dr. G. Chandramohan Reddy Garu, guest speaker of today's function, Dr. Srinivasa Perla Garu, Global Head Technical Training, Saint Hyderabad, Dr. Rameshwara Garu, Chairman IEI, Professor Ramanayak Garu, co-convener of the program, Engineer T. Anjay Garu, K. Guru Brahmam, other delegates and participants, good morning to one and all. Let me give a very brief introduction of our department. Mechanical Engineering Department of CBIT was established in 1979, along with the establishment of CBIT. At present, it's running 2 UG programs, Mechanical Engineering with an intake of 120, Production Engineering with an intake of 60. We have 2 PG programs also, one in Thermal Engineering, another one is CAD/CAM. Our UC and PG programs have been accredited by NBA. And one thing I want to mention proudly is 26 out of 47 of our faculty are doctorates. CBIT is always ahead of all private engineering colleges in the state of Telangana and previously in the state of combined state of Andhra Pradesh. And we have been working to retain our position in the first place. For this, let me tell you a few accomplishments of our department in the last 3 years. Our faculty have been awarded 7 sponsored research projects worth 98 lakhs in last 3 years, published 4 patents, 206 journal papers, 5 books in last 3 years. One of the prestigious projects we are working on is Artificial Heart in collaboration with Share India, Pittsburgh University, and Cornell University. In the current academic year, we have conducted 4 FDPs. Presently, our faculty are guiding 84 research scholars. In the last 3 years, 15 PhDs are awarded and 2 were submitted under the guidance of our faculty. Almost all eligible students of mechanical engineering are getting jobs through campus in companies like Accenture, HUL, L&T Infotech, Hack with Infosys Systems, ITC, Arabindo Pharma, Byju's, Hyundai Mobis R&D, Just Dial, TCS, Cognizant, Infosys, FMG Technologies, ZF Technologies, Godrej Boys Manufacturing Company, Dyson Technologies India Private Limited, Blue Star Limited, JK Paper Mills, and so many other companies. The starting salary of 3.6 to 12 lakhs per annum. I'm confident that in future we'll get more placement, better packages, because we're concentrating more on skill-based industry-specific training under able guidance of our principal, Dr. G. Pradasarathi Verma Garu. Thank you for giving the opportunity. Thanks a lot. Thank you, sir.
Thank you, sir. Today we are having our engineer Sudhakar, our past chairman, and also Brahma Reddy, our council member. If they want to tell anything, sir, Sudhakar, sir, you can also tell 2 words, Brahma Reddy and Sudhakar. Unmute yourself, sir.
సుధాకర్ గారు చెప్తున్నారా లేదు?
చెప్పండి మీరు చెప్పండి.
Only 2 minutes.
గుడ్ మార్నింగ్ చైర్మన్ రామేశ్వరరావు గారు, డాక్టర్ వర్మ గారు ప్రిన్సిపాల్, డాక్టర్ రవీందర్ రెడ్డి గారు, చంద్రమోహన్ రెడ్డి గారు. Because I'm not putting all designation, it takes more time. And really this program is manufacturing is very good. This type of programs actually we should conduct I think once in 3 months by bringing industry also into in collaboration with all our programs. And Dr. Rameshwara is really doing an excellent job by
Inviting.
bringing so many like CBIT, like some industry also who is in the manufacturing. Of course, Satyanarayana Garu is also there in that, but in some large industry, if it is brought, it will give more enlightenment and more light and boost to this type of programs. And I thank the chairman of the Telangana State Center and all the listeners to give me an opportunity to say a few words. Thank you very much.
Sir, please.
No, thank you, Chairman, sir. And this is a good opportunity to have provided me to speak. But stalwarts are there to speak. Whatever I speak, it will be very little. And I don't want to consume time of them. Anyhow, I thank you all.
Okay, very good. Thank you, sir. Okay, you want to also say anything, Ramnanak? 1 second.
Half second, sir. It's a highly appreciable program under dynamic staff of the Chairman Rameshwara Garu and Satyanarayana Sahab, Tirumon Sahab, and also Professor Verma Garu. Really great, sir. I have a little bit good touches with CBIT since a long time when Tirumon Sahab was there and Professor Chandrakesh was there. But really, CBIT is doing a lot of R&D programs, the lab to land, sir. Really, in this pandemic also, highly appreciable, sir. Congrats.
Just now I want to introduce our Dr. S. Satyanarayana, immediate chairman, past chairman, IA Telangana State Center. Dr. S. Satyanarayana, immediate past chairman, IA Telangana State Center, also served as the chairman and member of PRDB IEI. He relinquished the post of principal director and CEO of Center Institute of Tools and Designs, Ministry of MSME, Government of India, Hyderabad, to set up his own industry and to manufacture critical components and assembles to the defense and aerospace sector. These few words now I am requesting Dr. S. Satyanarayana, please chair technical session start, sir.
Thank you, Rameshwara. Shall we start now technical sessions? No? Then,
Sir, and also, sir, today I have forgotten to mention our Honorary Secretary T. Anjaya, sir. He is also there, sir. Because of I came very fast within 15 minutes. Cut about 2 years, sir. That's why I forgotten mentioning our name of our engineer T. Anjaya, Honorary Secretary, also in this webinar, sir. Okay, please, sir.
okay, Rameshwara, presiding officer of this function, and principal CBIT Sri Verma Garu, and head of the department Mr. Dr. Ravindra, and convener and speaker and professor and former principal MGIT, my good friend Professor CM Reddy, and my Srinu, my colleague in CITD, and today is global head of training in Infotech Enterprises. And we are also getting one more person, Mr. Suraj Vaishnav. He'll be joining around 11:30 to give some demonstrations about this digital manufacturing. And my friend, Mr. Anjaya, Honorary Secretary of Institute of Engineers, and Council Member Sudhakar Garu and Brahma Reddy Garu, and our Joint Honorary Secretary Ramana Nayak, and all other faculty members and my colleagues, everybody. Good morning to all of you. Today, I am really privileged to chair this one-day workshop on smart manufacturing, that is connected factories, being organized by CBIT and in association with the Institution of Engineers of Telangana State. This, because before going further, let me tell about Dr. Chandramohan Reddy. He's an expert. He's an expert in metal farming, particularly bulk farming. We have a lot of association with him. And when I was the principal director, he was doing his PhD and I was also doing my PhD, and the guide is common, that our Kamriya Sahab was the guide. way back, I think 1999 or 2000. We used to have a lot of introduction, and then I could understand, his capabilities as far as the metal forming is concerned. Bulk farming, he has done a lot of analysis and, a lot of new things he has invented. So this Chandra Mohan Reddy sir today is conducting this program and organizing, giving a, lecture on this is really useful for all the people, because it's not just an academic lecture. He would be mostly, covering practical aspects also. That is how, I am very happy to chair this session. And coming to this PSR, I call him as PSR because he was my colleague in CITD. He used to take care of CAD CAM and CNC machine shop. Now he is with the Scient, and he is a training head there. And is an expert in Industry 4.0 and 5.0, and particularly, the digital twins and digital thread technologies. And one more person is joining, Suraj Vaishnav. When he comes, no problem, I will explain about him. And he is joining and giving some demonstration about the digital manufacturing. So with these few words, I once again welcome all of you. And let me, share some of my views. In the initial stages, when the manufacturing was started, most of the manufacturing was done by skilled operators, fitters. They used to somehow do filing, scraping, grinding, and finally used to fit the component. There were no proper drawings, there were no proper tolerances, and machine facilities are also not there. But over a period of these 2 centuries, that is 200, various developments have taken place. We call it the first industrial revolution, when the water power, that is hydraulic power and steam power is utilized. We call it the first industrial revolution. And then electricity has come into existence, and electrical power is enormously used for production of the components. We call it a second industrial revolution. And when, the IT and computers have taken, a lot of everywhere, then we call it as it has also entered into manufacturing area. So this foray of this IT and computers into manufacturing has totally revolutionized the manufacturing systems and manufacturing process. That we call as a third industrial revolution. And everybody is saying that today we have the fourth industrial revolution, and also fifth industrial revolution also has entered. People are talking today Industry 5.0. So during this 2 centuries, various manufacturing strategies have been adopted, like mass production. Every one of you know, mass production, there used to be only special purpose machines. Computers were not there. Every component used to have its own machine, and that is useful only for that. It is a rigid machine, it's not a flexible machine. Then lean manufacturing, then flexible manufacturing. So same machine can be used, there are general purpose machines. Same machine can be used for various components. And then agile manufacturing, reconfigurable manufacturing, predictive manufacturing, cyber manufacturing, and mass manufacturing. These all the realized mostly because of these developments in the computer science, mostly computer science. Like internet. Somebody, I think somebody is talking. It is mostly because of the Internet of Things, advanced sensors, industrial big data, adaptive machine learning, cyber physical systems, etc. And also material science has taken vast developments, particularly the optics and nanotechnology and development of lightweight materials. All the things have taken a big role in manufacturing area. Today, we are all talking about additive manufacturing, 3D printing. My chairman Rameswara is also telling 3D printing. There is a 3D printing equipment available in ISKI. And if anybody from CBIT wants to go there and do any experiments, it is open to all the people. So this kind of technology, this is the latest technology. And the robotics, development in the robotics. Wherever the man is, it's dangerous for the man to go there and operate in an environment where it is like very hot and polluted environment. The robotics are being used, and distributed and cyber manufacturing. This is a very, very important manufacturing. Today, what is happening is there are apps coming. Like today, if you have to manufacture a component, we have to design the component, do prototype, and give it to a machine, and it is done on a CNC machine. But with this technology, this cyber manufacturing technology, apps are available, and like any other app, you can book your ticket, or you can maybe you can order your on Amazon. This kind of apps are available, or Zoom app. This kind of apps are going to come, wherein you can manufacture the component on your own. You can design the component, whatever shape you want, whatever fashion you have. According to your fashion, you can design the component, and that component can be manufactured by yourself itself. Because there is an app, the moment you design the component and apply the app, it will generate the 3D programming, and it will go to 3D printing machine. Once 3D printing machine will print the component and give it. Printing in the sense manufacture the component and give it. This is a very, very advanced technology. And one more thing is hybrid process. Earlier, this 3D printing we talk, it is a additive manufacturing. And when you come to the machining, it is a subtractive manufacturing. Today, both the things are, inbuilt into one system. This system, is called hybrid manufacturing. You can do both subtractive manufacturing and additive manufacturing. And this is the great advantage, particularly for the environment and saving the materials and, other aspects. And the lightweight materials have also come into picture. And one more is multi-scale process. Here, what happens, some of the aerospace industries, you want only 1 or 2 items. Defense, you want only batch production. When you go to automobile products, you want millions, mass production is required. All these things now, for your layout for a mass production is different, your layout for a batch production is different. But whereas this kind of things are combined together, and multi-scale process today have come into play. They like macro, meso, micro, and nanoscale manufacturing process methods have already been being adopted. And one more is predictive analytics and infotronics for intelligent maintenance systems. The machines are today very smart machines. They can understand and they can tell you what is wrong with that. They can say, yes, already my capacity is over, or I am ready for maintenance, or my temperature has already gone up. I want to take rest for about 5 minutes so that my temperature will come down. So this kind of smart machines are coming, and because of the smart machines, predictive analytics and infotronics in the maintenance systems have given zero downtime almost. That is one more advantage. And I just want to tell you about this reconfigurable manufacturing systems. So this is now what is happening is, when you go for a system, you purchase a machine over a period of time, because of the obsolescence that is playing a vital role today in the development. Because of the obsolescence, that machine should not go waste, and that machine should be used for something else. So there is reconfiguration of the machine tool is being done, so that the capital equipment that has gone into the machine tool purchase will not go waste. So this kind of systems are also coming. One more is remanufacturing systems. Today, everybody is talking of the ecosystems. That is eco-friendly and pollution-free and environmental friendly. So this kind of things, what is happening is, whatever the manufacturing systems you are using or whatever products you are using, that should be converted to again some other utility. It should not go waste. It should not become a pollution problem. So this kind of remanufacturing systems are also coming. So this is one thing where this I think probably people have to understand. And one more is real-time 3D machine vision. Machine vision, that is for manufacture for inspection purposes. And all the things are one aspect. When you talk of the digital factory, I just want to share maybe 1 minute, 2 minutes. I don't want to take much of the time. Already it's 10:15. See, earlier we used to make on a drawing board. We used to make a orthogonal production and isometric view. Today, because of the CAD systems, we are able to build a 3D model, and we are able to do analysis and simulate whether its functioning is good or not, whether any modifications are required. So these are digital models are being created. Like the digital factories are also coming. So with the advantage of digital factories, what happens is, the digital factories generally, this is with virtual realities playing a very important role, and IoT, Internet of Things, are also playing very important role, and 3D modeling. All the things put together is called digital factory. With the digital factory, what we do, we need not set up. We need not set up the factory in advance. What you have to do is, when any requirement is coming from the customer, you send it to digital factory and see that virtually, you see that whether the component is useful for us or not, whether the component is serving the purpose, and we are able to manufacture the component within that cost. All the things can be done in a digital factory. So this digital factory is a lot of advantage today it is playing, because it is cutting the time. There is a concurrent engineering is also playing, because parallelly you can develop the component, at the same time you can analyze and simulate the component and do all sorts of checks, right? Not only the visibility, functional checks and cost analysis, everything you can do. This is what is digital factory. And the digital factory, digital technology, when it is now actually extended to the manufacturing, it has become a smart manufacturing systems. So today, smart manufacturing, let me just share some of the things. All of you are aware, Fitbit or Apple Watch. Apple Watch, no? We are hearing Fitbit and Apple Watch. So this what happens now, when you wear a Fitbit or Apple Watch, it will tell you, control over your personal lifestyle by providing real-time data about your activities. Sometimes, it will tell you what is your BP level and how much is the sugar level and how much, exercise you have done. These all the things are connected. These all the equipment, this digital equipment is connected to our human body, and it is giving feedback to our human body, so that when you are going upstairs, whether you have to take an escalator or going by stairs, so that you can decide, yes, it will tell you go by escalator, so that you can burn some of your calories, or don't burn any more calories, you are already exhausted, take an escalator. So this kind of technologies are already available for a human body. The same thing is extended to now factories, manufacturing system. That is a connected factory. Okay, because they're all explaining all these things. So this kind of connected factories and digital technologies and digital things and digital thread technologies, our PSR is very expert in this, and probably we'll be listening to him. With these few words, I once again thank our Chandramohan Reddy garu for giving me this opportunity to chair this session. Now I request our course convener, Sri G. Chandramohan Reddy garu, Professor, CBIT, and also speaker for today's thing, to start his explain about the program, today's program.
Thank you, sir. Thank you, Dr. Satyanarayan garu, for the kind introduction. And respected Dr. G. Rameshwara garu, the chairman of Institution of Engineers, Telangana State Center, and our own respected council members, Dr. G. Sudhakar, Dr. Brahma Reddy garu, and our own Dr. Satyanarayan garu, immediate past chairman, and engineer Anjay garu. And we are also seeing Mr. KNS Prakash Rao in the line from Vizag. Good morning, Andy. And there are several other colleagues from IAA side and from CBIT. We are extremely grateful to the principal, Dr. GPS Varmagal, for the kind support in organizing this program. And of course, our own Dr. P.V. Ravindra Reddy and my colleagues from the department. And there are ME CAD-CAM second semester and fourth semester students who have joined in this particular program, apart from the junior colleagues. So I extend a hearty and warm welcome to you to this program. So in particular, when the pandemic has started in April 2020, we were all asked to complete certain courses during the break. So I have selected to do the course on digital manufacturing and design from New York State University, and I have completed 2-level courses in digital manufacturing and design. The reason was I was also teaching digital manufacturing. Theoretically, it was okay, but I wanted to have some practical interface. So that's how my journey into digital manufacturing has started. And digital manufacturing, the smart manufacturing and connected factories, and then Industry 4.0, they all go together. The smart manufacturing has been defined as the fully integrated collaborative manufacturing systems that respond in real time to meet changing demands and conditions in the smart factory, in the supply network, and in customer needs. Improve manufacturing asset efficiency and avoid unplanned downtime with the data analytics, avoid manufacturing machine failures, and reduce maintenance costs with the machine learning and industrial Internet of Things, data analytics, machine equipment failure. In every way, this particular technology is useful. Service pack optimization. That is about the smart manufacturing. And when you talk about connected factory, a connected factory is a manufacturing facility that uses digital technology to allow seamless sharing of information between people. See, the digital manufacturing is known for the transparency that is made available to the lowest level shop floor employee in the company, right from the CMD. So the seamless sharing of information between people from top to bottom, machines and sensors. There are two main goals to enabling connectivity in a plant or factory. The other goal of the connected factory is to empower workers on the shop floor. Because whatever the level of information the CMD of the company or the MD of the company, executive director of the company are having with regard to the products that are being developed, the shop floor personnel will also have the same updated information. In the absence of digital manufacturing, it is not possible. So by connecting devices to the manufacturing process, connected smart factory helps manufacturing companies to better predict and resolve maintenance requirements and correlate quality issues to machine and environmental factors, reduce downtime and improve quality. Are you all listening? Is it okay?
Okay, okay, sir. Okay.
Right, sir. Thank you. One moment.
Chandramohan, go for slides.
Yeah, I'll start, sir. The smart factory is a concept of expressing the end goal of digitization in manufacturing. The way the term is most commonly used, a smart factory is a highly digitized shop floor that continuously collects and shares data through connected machines, devices, and production systems. So with this background information, I will start my presentation. So I hope you are all seeing my PowerPoint presentation. Is it visible to you?
Yeah, it is visible. You can go ahead.
So this is of course, the title sheet which you are seeing. Anyway, I will do one thing. I will stop my video so that I will have better streaming with regard to audio quality will be enhanced when I stop my video. Okay, that's fine. Yeah. Just a moment. Yeah. Basically, I'll be speaking about Industry 4.0 and digital manufacturing. They go together. This is the presentation. I roughly made it for presenting for about 60 minutes. So I hope to complete it in 60 minutes. So what is Industry 4.0 manufacturing? Is it automation or some electronics or integration of software equipment and people? Of course, all these will be there in what form and what shape and how it happens. Let us see. Industry 4.0, why it matters? See, whenever you want to get some answer, the question should be better. The better the question, the better the answer, the better the world works. And the agenda for this discussion is industrial revolution that is actually caused this Industry 4.0 to happen. That's nothing but the fourth industrial revolution. There are a number of building blocks of Industry 4.0. In my presentation, we will discuss them. And potential industrial products implications, potential consumer products implications, and the impact of Industry 4.0 in the overall manufacturing also we will see. And what is this? I think all of you must have seen in your village or at home. This is being used is a wet grinder. This is being used for good old days. And this also, you know, the concept of making is some small turbine arrangement to draw the water or to utilize the water to generate the energy, vice versa. Both the cases, this is being used. And of course, this is a floor mill, and you are all aware. When we were young, we have seen this. And of course, this is automated rice mill. Some level of automation you can see in this. And then why? One can design, but the design may well be impossible to manufacture. That what are the forces behind this transition from different levels? What is it actually driving? Let us see in this video clip, I mean, as it explains.
In this lesson, we will be focusing on why the transition from traditional manufacturing to a more integrated digital approach is happening. After this lesson, you'll be able to identify and explain at least 3 business and technical advantages of the DMD approach. A major force driving the transition to digital manufacturing is economics. It's no secret that the U.S. leadership in manufacturing has been eroding over the past few decades. What may not be known is that in 2001, the U.S. trade balance for advanced technology products went into a deficit. This has multiple impacts, including jobs, the overall economy, and future competitiveness in advanced products. When the U.S. loses our manufacturing base in advanced technology products, we then lose the ability to innovate on the next generation of those products, setting up a downward spiral. From a business perspective, digital manufacturing and design benefits beyond impacting the balance of trade. For first-to-market advantage seekers, digital manufacturing and design allows for product design and manufacturing design to occur simultaneously, reducing the time required to go from concept to product. Another benefit of digital manufacturing and design is shorter product life cycles that address accelerated technology obsolescence. An example of this is how fast product lines are now turning over, like having new phone models every year. On the web 15 years ago, it took 3 to 5 years before a website was obsolete. Today, that's been reduced to 14 to 18 months. Obsolescence could be an entire topic to itself. For those interested in learning more, we have included some additional resources for more in-depth exploration of the topic as part of this course. A third benefit is addressing the social and political factors driving job creation and retention, often referred to as reshoring. As has occurred in other emerging economies, labor costs have increased in China by 13.7% between 2000 and 2015, making manufacturing outsourcing less attractive. As a result, there is now an opportunity to bring manufacturing back to the U.S. In addition to business reasons, digital manufacturing and design promises to overcome some key challenges facing the traditional approach to manufacturing. These challenges are the physical separation of designers and makers has slowed innovation. Digital manufacturing promises to overcome this by creating real-time digital links between designers and makers. A second challenge is that barriers to sharing data and information have existed, both in terms of IT infrastructure and in terms of incentives, skills, and IP policies. Labor costs are continually increasing, not just here in the US, but globally as well. And products are increasingly integrated and complex. These challenges can be overcome by using digital manufacturing to create.
So just now you saw why we should transit from the traditional to the, what are the forces behind, which are actually pushing us to take up this digital manufacturing. Now, what is digitization? The next slide is explaining about the digitization. digital information from multiple sources, formats, etc., to address key challenges of society in various aspects, such as health, education, weather, transport, commerce, government, and then manufacturing, etc. In every sector, the digitization is playing a key role. And then you have what is manufacturing. See, I have been very much fascinated by this term manufacturing. I have been very much interested in it because manufacturing is a big term. It encompasses, there is a small term manufacturing and there is a big term manufacturing. The manufacturing is a process for converting ideas and market or customer needs into artifact. That is big manufacturing. See, earlier, soon after the independence, we were importing the technology, and the shop floors are meant for producing the components. So therefore the term production was there. That is little m manufacturing. So that's nothing but the conversion of raw materials into useful products. The traditional definition, what you observe on the shop floor is where work orders and machine instructions are converted into hardware. That is the production aspect. When you say big M manufacturing, it's a whole comprehensive term, right from idea creation to the final product and product disposal also. See, most manufacturers, they don't mention about the product disposal. That's very, very important. In digital manufacturing, we take the whole cycle of idea creation to the final product and its utilization till its lifetime, and its disposal is also included in that. That is big M manufacturing. Then historical development of integrated manufacturing, if you see, is a manual manufacturing first, and then followed by mechanization. Mechanization is the first industrial revolution where water power and steam power was used. And then next is the automation, mass production, assembly line, and electricity. You can refer roughly to the years 1920s. And then computer and automation, the so-called the third revolution, Industry 3.0 is nothing but the third revolution where NC and CNC have come in a big way, including FMS. But the fourth industrial revolution is due to the integration of cyber physical systems. Apart from the automation is combined with the internet. Availability of the cyber system, the cyber technology made this Industry 4.0 possible. And then now we will see this fourth, the industrial revolution, Industry 4.0. Here again, there is a small clipping through which you will understand many things.
Welcome to the first course, Specialization in Making Products. After completing this lesson, you'll be able to explain what is meant by digital manufacturing, and also explain how digital manufacturing and design represents the fourth generation of the Industrial Revolution. To set the stage, let's take a step back to the first Industrial Revolution, ending in the early 1800s. This transition is often thought of as the Industrial Revolution, but is actually the first of an ongoing sequence. The first Industrial Revolution was represented by the transition from manual production to mechanical production, enabled by the harnessing of water and steam power. The second Industrial Revolution came at the beginning of the 20th century, with the development of approaches that enable mass production, including the assembly line. The third Industrial Revolution, also known as the Digital Revolution, represented the advances made possible by automation as mechanical and analog technologies gave way to digital electronics between the 1950s and the 1970s. We are now entering what is being described as a fourth revolution, also known as Industry 4.0. Industry 4.0 is the next phase in the evolution of manufacturing, combining the cyber capabilities resulting from advances in computing with physical systems to create a highly intelligent, interactive, and automated manufacturing ecosystem that integrates product design, manufacturing, and logistics. Now, a formal definition of manufacturing is the process of converting raw materials, components, or parts into finished goods that meet a customer's expectations. Manufacturing is the most tangible part of the product lifecycle because it results in a clear outcome. There are multiple definitions of the product lifecycle, most differing only in their terminology or details. For this course, we'll use the definition provided by Michael Greaves in his 2006 book, Product Lifecycle Management, Driving the Next Generation of Lean Thinking. Greaves defines the lifecycle as all aspects of a product's life, from its design through manufacture, deployment, and maintenance, culminating in the product's removal from service and final disposal. The first stage in a product's lifecycle is planning. This is where designers work through understanding requirements, whether they come from customer expectations, industry standards, or regulations. These requirements are then transformed into specifications, or technical requirements that can be measured. These specifications give you a way to evaluate initial feasibility of a product and whether the process should continue to design. Design is the product lifecycle stage where form and function come together to meet specifications. As you develop prototypes, whether physical or in a computer, design is where parts are created to fill the needs of the product. This begins in an abstract fashion with conceptual design and concludes with detailed design, where final detailed part specifications are created. The next step of the process is to take the product from a design and build it. This stage includes when you define the items that need to be manufactured and how they'll be created and assembled. Production prototypes are created and checked to see if they meet performance and cost requirements, as well as long-term production capabilities are established. This is also where customers have a chance to evaluate the acceptability of a manufactured product. Once produced and purchased by the customer, the product must still be supported. The support stage of the life cycle is where you provide the customer with information to assist in the effective use of the product and maintain the operational performance of the product. A product's life cycle ends with disposal and recycling. The dispose stage of the life cycle draws on information from the design and build phases to understand the composition and what portions of a product can be recycled into future applications. As with other stages, the dispose stage may iterate with design as you work to develop a product that meets performance expectations and that can be disassembled at the end of life. Over time, multiple opportunities for improvement have been identified for traditional design and manufacturing processes. In a product's life cycle, many iterations may be required before customer approval is received. In traditional paper-based processes, information sharing can consume valuable time and delay the development process. In traditional processes, there is also a lag during and in between stages in the life cycle as necessary approvals are sought. Sometimes, this can even result in losing first-to-market competitive advantage. Another challenge in paper-based processes is that maintaining a single source of truth for product and process definitions is very difficult and can result in limited capabilities for data analysis and evidence-based decision-making. Communication problems can result when planned changes are made during design and development process, as well as after the production launch.
This
A
is one
new
important
approach
area
is
all of
digital
you should
manufacturing.
remember.
This approach uses increased computing power to improve the product lifecycle. The Digital Manufacturing and Design Innovation Institute, or DMDII, defines digital manufacturing as an integrated suite of tools that work with product definition data to support tool design, manufacturing process design, visualization, modeling and simulation, data analytics, and other analyses necessary to optimize the manufacturing process. Deployed throughout the product lifecycle, digital manufacturing enables you to more quickly and authoritatively share information in the design process, with all the data generated in every part of the lifecycle representing a digital thread. This digital thread can be used to create a computer-based digital twin, an integrated system of data, models, and analyses that can be used in design, manufacturing, support, and disposal. These concepts all come together as the fourth industrial revolution, Industry 4.0. An example of the vision and promise of Industry 4.0 can be found in the wind power industry. Wind power is an important component of the clean energy industry. An ongoing challenge for wind farm operators is the significant wear and tear of gearboxes. Gearboxes are expensive to fix, especially after failure. However, if sensors on the turbine are linked with weather information and computational models, a very accurate simulation can be developed for each individual turbine, enabling evidence-based decision-making and the creation of predictive models for performance of individual turbines and the wind farm as a whole. This concludes the first lesson of digital manufacturing and design.
So just now you saw what is digital manufacturing, the understanding of digital thread and digital twin. Now, once again, this slide explains in detail about the industrial evolution that has taken place. The first industrial revolution, introducing mechanical production machines powered by water and steam, that is called, towards the end of the 18th century, it is called Industry 1.0. Then second industrial revolution, introducing mass production lines powered by electric energy, that is called Industry 2.0, that has happened around the beginning of the 20th century. Then industrial revolution through the use of electronics and IT, further progression in autonomous production, that is Industry 3.0, that is beginning of 1970s. Next, industrial revolution 4, that is based on cyber physical systems integration, that is Industry 4.0, that is as on date. And here I would like to mention that in Industry 1.0, 2.0 and 3.0, our participation was not there because Industry 1.0 and 2.0 happened prior to the independence, and Industry 3.0, though it has happened after independence, we were not there. But when it comes to Industry 4.0, we should be proud as Indians that we are very much part of the Industry 4.0 evolution, its revolution, and its development. We are there everywhere in every aspect of Industry 4.0. And let us feel proud that as Indians, we are there very much in Industry 4.0 and its developments. Of course, once again, it is showing year-wise distribution, how it has happened 1760 to 1840, and again 1870 to 1940, 1960 to 2010, like that. You know, what is the development and technological innovations that have happened in the years, year-wise it has mentioned. And then we have Industry 4.0. If you take some worldwide examples, in Germany, there is a smart manufacturing leadership coalition with USA, a collective term for technologies and the concepts of value chain organization. And let me tell you one particular thing here, that no two cases of digital manufacturing are same. Everything is unique based. So based on the technological concepts of cyber physical systems, the Internet of Things and the Internet of Services, it facilitates the vision of the smart factory. Within the modular structured smart factories of Industry 4.0, cyber physical systems monitor physical processes, create a virtual copy of the physical world, and make decentralized decisions. Over the Internet of Things, cyber physical systems communicate and cooperate with each other and humans in real time via the Internet of Services. Both internal and cross-organization services are offered, utilized by participants of the value chain. This is possible as it builds on the digital revolution, smaller and powerful sensors, machine learning concepts, ubiquitous internet means abundance, availability, and everywhere of internet, artificial intelligence, and of course with the labor and energy cost. Then if you see, take 2006 as the specific year. In 2006, iPhone was not there, iPad was there, Kindle was there, not there, 4G was not there, Uber and Airbnb and Android, which we are using, one of the most mobile operating system was not there. But if you see the Android, Instagram, Snapchat, WhatsApp is also not there. These are all not there. But if you see time to reach 100 million customers, telephone, it took 75 years to reach 100 million customers. And the World Wide Web, it took 7 years to reach 100 million customers. Facebook took 4 years to reach 100 million customers. Instagram took 2 years. And Pokemon Go, the video game meant for children, it took 1 month to touch 100 million customers. So evolution of the desk, you can see the size of the, see, 1980s, it was a big box, very big size. Now you see the size of the laptop, 2014 onwards, very sleek. Okay, this is how the technology has made brought in several revolutions. Cyber physical systems, as I told you, cyber physical system is a system of collaborating computation elements, controlling physical entities. The cyber physical systems are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with the physical processes. See, today's factory, everything is happening in a sequence manner, rigidly sequenced. Say, for example, if you take car manufacturer and a production line, so it goes from workstation 1 to 2, 2 to 3 in a sequenced manner. But if you see the tomorrow's factory, it need not be. It is completely decoupled, fully flexible, and highly integrated manufacturing systems. So it can go crisscross anywhere. You know, the product sequence is decided by for every product it is different. Product A can pass through 1, 2, 3, 4. Product B can go 1, 3, 4, and then 2, like that. It can happen. So that is what is going to happen in tomorrow's factory. Oh, one moment. Sorry. So Industry 4.0, it consists of mainly 6 design principles: interoperability, the ability of cyber physical systems, that is workpiece carriers, assembly stations, and products, humans and smart factories to connect and communicate with each other via the Internet of Things and the Internet of Services. Virtualization, a virtual copy of the smart factory, which is created by linking sensor data with virtual plant models and then simulation models. And then decentralization, the ability of cyber physical systems within smart factories to make decisions on their own. Then real-time capability, the capability to collect and analyze data and provide the insights immediately. Service orientation, offering services of cyber physical systems, humans, and smart factories via the Internet of Services. Modularity, flexible adaptation of smart factories for changing requirements of individual modules. These are the 6 design operating principles of Industry 4.0. And these are the building blocks of Industry 4.0.
The Internet of Things has the potential to increase global productivity up to 25% by 2025, which could translate to an economic value of $11 trillion. Industries like manufacturing are embracing the potential of the Internet of Things. Many production facilities are already using processes and supervisory control systems with connectivity. The Internet of Things for manufacturing is a family of solutions that combines the capabilities of analytics, cognitive computing, and the Watson Internet of Things platform to drive operational efficiency across the factory value chain. This solution benefits the manufacturing industry in 3 main ways. First, it helps plants get 100% efficiency out of their equipment by identifying and solving issues before they cause delays. Second, it makes processes and operations cognitive, so plants can produce maximum quality and yield from raw materials and manufactured components. Lastly, it helps plant managers better manage resources, improve worker expertise, and provide a safe working environment. Advances in these 3 areas define a new wave of connected manufacturing, one that revolves around things, process, and people. Let's take a look at how this works for Simon, the plant manager for an aircraft manufacturer. Simon oversees the production of key components for large commercial aircraft, and his top priorities are meeting production deadlines and producing airplane parts safely and efficiently. One of his biggest clients needs to move up their delivery date by 3 months. Simon and his team use the Internet of Things for manufacturing, which will help them deliver earlier than originally planned. An equipment analytics solution identifies problems with equipment health and performance before they happen and prescribes maintenance procedures so Simon's team can avoid equipment failure and downtime. getting maximum effectiveness out of their equipment. To ensure the components are meeting quality standards along the production line, Simon uses a quality analytics tool to identify variability in the manufacturing process in real time. This allows equipment operators to make adjustments to process parameters based on plant conditions that could affect the quality of production. By monitoring quality in real time, Simon's team can avoid producing faulty components, ultimately saving time and money. Another priority Simon has to account for under a rush schedule is the safety of his plant workers. The cognitive IoT platform includes worker safety technology that monitors things like exposure to extreme heat or toxic gas, open flames, and operating dangerous machinery. The plant workers wear sensors in their helmets and wristbands that provide real-time alerts on working conditions, activating preventative measures if physical well-being is compromised or safety procedures have not been applied. Because the platform allows Simon to track all of this Internet of Things data in real time, he can be confident that the production equipment, tools, and employees will be able to safely take on an accelerated schedule and make plans to move forward. Once the completed aircraft from Simon's plant is put to use, those manufactured parts continue to generate data over time, data that designers and engineers can use to make improvements and updates to each part in the future. Additional sensors also make it possible for Simon's plant to offer cognitive solutions to the airline to help with ongoing predictive maintenance of each manufactured part. Using the power of the Internet of Things paired with cognitive computing and analytics, companies across all industries will improve the way they design and manufacture connected products. Products that will change the way we work and live.
Okay, that is about both the slides. When you can see the one side what happens inside a factory, and the other side the concept of connected factories. So you have seen this. Let us go to the next slide.
The Internet of Things.
And this will impact this particular Industry 4.0 technology, or in the digital manufacturing, will impact in all aspects of value chain, right from the engineering, design tools and simulation to the up to the human resources on one side, and material, and then sensors, actuators, and industrial control systems. Everywhere the impact will be felt. And then, of course, when you see the value chain, how this digital manufacturing and design, multiple organizations in the manufacturing, how it is going to impact. And this is once again, there is a small video clip. Of course, we have almost come to the end of the presentation. In another 10 minutes, it will go over.
The effects of digital manufacturing and design on the ability to manufacture products, especially when multiple distributed organizations are involved. Let's consider something simple, like this pen. This pen is a BIC Pilot G2. BIC is the organization that manufactures the end product, what we purchase. A term for BIC's place in the enterprise that creates this pen is the OEM, the original equipment manufacturer. The OEM relies on suppliers to manufacture and deliver components that can be assembled. These suppliers purchase component parts from other suppliers. This can repeat many times, getting to the most basic components of a product, like the ink in this pen. These suppliers are referred to as Tier 1 suppliers or Tier 2 suppliers, etc., referring to their place in the structure that provides components that are assembled into the pen. The supply chain refers to the system of organizations involved in creating a product. Products of any size have a supply chain. Consider the Boeing 777, a very large and complex airplane. As the OEM, Boeing manufactures the final product. In order to manufacture this end product, Boeing purchases large shock-absorbing assemblies from a Tier 1 supplier, ITT Enidine. ITT Enidine purchases machine pistons from a small machine shop and gets them chrome-plated at a small plating shop to enhance surface properties. The machine shop and the plating shop are examples of Tier 2 suppliers. Next, we have two videos that highlight concerns that can result from a complex supply chain. Please watch the videos and take a moment to consider their impact. For the 777 to be manufactured with the right quality in the right amount of time and at the right cost, it is critical that all organizations in the supply chain communicate effectively. This communication includes timely information sharing with the right stakeholders. Rather than relying on paper documents, a digitally enabled supply chain allows design documents, part revisions, and purchase orders to be shared electronically. Redesigned components can be checked for fit without having to produce a single part, saving significant time. A way to think about this impact of the DMD paradigm is the right data in the right place at the right time, enabling quick and correct decision-making. This focus on the timeliness of data reduces the impacts of a change that can lag in time and grow in scale as it propagates through the system. Sometimes this is known as the bullwhip effect. An example of this is how, in 1994, a strike at a single brake plant ended up shutting down major portions of GM's vehicle production. DMD reduces the effects on the supply chain by transparently sharing efficiency information, whether man, machine, materials, or methods, throughout the supply chain, increasing supply chain confidence between tiers, reducing excess inventory that's contained within the supply chain, and allowing for realizing more efficient and agile supply chain models. This lesson described the impact that DMD has on the supply chain.
Sir, we are not able to hear. Voice is not coming. Chandramohan Reddy, your voice is not coming. Hello?
Yeah. Now, sir, how it is now?
Now it's okay.
Now it's okay. Okay, sir. Thank you, sir. Thank you very much. This entire value chain is digitized and integrated. So you can see the steps in the product design to the services stage. So different stages, there are different simulations and automation, and there are the integrated aspects are there. And then potential implication of this digital manufacturing is robot-assisted production, predictive maintenance, additive manufacturing of complex parts, machines as a service, big data drive quality control, production and simulation, and the smart supply network. Then you can see the robots, how robots are placed in Amazon warehouse from year 2013 to 2016. You can see 2013 they are less than 5,000. And you can see in 2016, there are 45,000 robots are placed in one particular example. And if you take the Siemens example, German manufacturing giant Siemens, an industrial user, is implementing an Industry 4.0 solution in medical engineering. For years, artificial knee and hip joints were standardized products, with engineers needing several days to customize them for patients. Now, new software and steering solutions enable Siemens to produce an implant within 3 to 4 hours. This is due to the customization that is possible. See, all humans will not have the same knee. So therefore, the customization is the key here. So this is made possible through this digital manufacturing route. And Trump is another one, is the tool maker and Industry 4.0 supplier and worldwide market leader of laser systems, has put the first social message to work. Each component is smart and knows what work has already been carried out on it. Because the production facility already knows its capacity utilization and communicates with other facilities, production options are automatically optimized. These are certain examples that I will show. GE is another example. This uses predicts the operating system for the industrial internet, is powering in digital industrial business that drive the global economy by connecting industrial equipment, analyzing data, and delivering real-time insights. Predicts-based apps are unleashing the new levels of performance of both G and non-GE assets. So this is another example. And of course, this is again, certain repetitions are there, which I'll be skipping. So these are the best examples of product evaluation, connected and smart factories, So these are all the products. These are all called as smart products because, say, for example, users can control Philips lighting light bulbs via the smartphone, turning them on and off. So yes, hello. Are you able to hear?
Yeah.
Are you able to hear me?
Yeah.
Okay, sir. So here, product design, the cost, if you look at it to product design, 5% material, 50%, 15% labor, and overhead is 30%, machines and all. But who casts the biggest shadow? Because the product design, if something goes wrong, if the product, see, it will influence to the product to the extent of 70%. The material influence is only 20%, though cost-wise it is 50%. Labor 15% cost-wise, but its influence is 5%. You can see overhead machines and all, cost-wise 30%, but influence-wise it is 5%. Therefore, product design is very, very critical. At the product design stage, you need to carry on. You have to have the interaction between the makers and the designers. And this the much needed transparency is very much provided by the digital manufacturing. Of course, big three in a production cycle: design, production, and process cycle. This is a very much a known slide. Of course, activities in a production cycle, I need not repeat this: design, production, planning, and then production. Same thing can be replicated, making use of the CAD/CAM also. In the case of CAD/CAM, you can say that that is the CAD and CAPP and then CAM. And then there are the boundaries between functions in traditional manufacturing. See, redundant data causes manufacturing problems. So this redundant data and related errors can be eliminated using. And this is how the information flows from design to production shop in any system of manufacturing. So here, the information sharing is very, very key to the digital manufacturing. And let us have a small pay for about 2 minutes only.
We get to the topic of how information gets shared between groups, whether machines, suppliers and manufacturers, or customers. After the lesson, you'll be able to explain the role of data and purchasing communication standards in manufacturing and design, including real-world scenarios where these standards can be applied. Why are standards relevant? Why do we need to be aware of the technical details of transferring information? Consider a simple example, a single manufacturing shop floor. The shop floor has several computer systems and manufacturing equipment of varying ages, each generating different output. The individual pieces of equipment are creating data in different formats for various reasons, like systems from different manufacturers have output in proprietary formats as part of an effort to lock in future software and hardware purchases. However, if we need to establish a relationship between two different data sets to create information or connect machines from different manufacturers, they cannot be in different formats. That's what data standards do. They specify a consistent data format so the data can be shared and transformed into usable information. Some examples are STEP and IGES are data standards for sharing product design data like geometry. MT Connect is a standard that supports the capture and sharing of information from machining equipment. MIL standard 31000A and ASME 1441 define a way to share product model information using a technical data package to support the product lifecycle. To complete learning about standards and their place in the digital manufacturing and design paradigm, we're sharing 2 additional items in the resources section. The first is a video on MT Connect.
So therefore, for the information sharing also, the protocols and standards are a must. That is what is shown in this particular video. And of course, there are common database for manufacturing systems. There are many overlaps as shown in this particular image. And then, of course, common database, see, the human resources person, the production person, business and engineering, they always get the same with regard to the product data that is made possible due to the transparency offered by the digital manufacturing. Of course, this sheet and these aspects we have. Of course, the product life cycle is very, very important. The life cycle considerations in product design are very, very essential as presented in this slide. And then, see, if you see the manufacturing trend, this mass production is mostly, you are moving towards the mass customization. Suppose if you buy the car, two individuals may prefer to buy the same brand and same car, but yet they wanted to have different preferences that is made possible by this manufacturing mass customization at no extra cost. See, even if the cost is extra, it should not be more than 5% of the basic price. So that is done by that is achieved by the mass customization. See, mass production versus mass customization. Earlier era was the mass production. Now we are entering into the era of mass customization. So this is going to impact the economy, the business at the national level and the global level, and individually and the society. This see, we have been hearing that with the automation implementation in IT, we are going to worldwide. We are going to lose jobs to the tune of nearly 30 lakhs. That is what is reported in the paper today and yesterday. So definitely the digital manufacturing also when implemented, it will have its own impact, but the roles will change. The roles will change and it is going to impact the economy. There will be growing and then aging of the old technology, old machines, they have to be removed. Removal of obsolescence is a must and the productivity will be enhanced. Employment will be generated, but these people have to be trained in the new technology. The nature of work changes and the labor have to be substituted with those who are trained in the new technology. So it is going to impact the business also. Customer expectations will change and then there are data enhanced products, so the collaborative innovation, new operating models will come into picture. So of course, there is a need to, how it is going to impact the workforce is presented in this particular slide.
Specializing in individual components of a product, like the suspension system of a car. Eventually, workers are seen as a blended workforce, where the focus continued to be on the manufacturing skills an employee might have, with some post-hiring training in continual quality improvement, like understanding the principles behind Six Sigma, or learning to operate multiple machining centers to increase efficiency. Operators are still seen with an open-loop perspective. The focus is on my machine, just processing materials to generate output, without any opportunity for feedback to impact the end product. Digital manufacturing and design envisions a workforce highly engaged with the creation of the product. From invention through to disposal, workers will need to understand how their actions impact design, manufacturing, and logistics. Workers will also need to use analysis tools and advanced machining to efficiently produce products, especially in a mass customization environment with a high mix of products, each with a smaller batch size. These changes shift the focus for digital manufacturing and design from only tooling and machining skills to workers that also have skills in technology, operations excellence, and people skills, or the ability to effectively collaborate with others as part of a team. Some items to keep in mind when considering the impact of the digital manufacturing and design paradigm are: the National Institute of Standards and Technology, or NIST, estimates that 600,000 manufacturing jobs are unfilled in the United States because of the lack of high-tech manufacturing skills among job seekers. According to the Society of Automotive Engineers, SAE, over 98% of all products will be developed digitally by 2020, which makes this skills deficit even larger. Small and medium-sized enterprises, SMEs, consisting of 1 to 500 employees, represent 95% of our nation's manufacturers. But 94% of SMEs have not adopted high-performance digital manufacturing practices. All this means that the opportunity to create a new generation of a workforce that is excited about and competent in digital manufacturing and design methods is very real. This shift may result in changes in job titles. Manpower is working with the DMDII to identify and update job titles impacted by Industry 4.0. Titles and responsibilities for drafters, CNC programmers, machinists, especially those using manually controlled equipment, document control specialists, inspectors, and testers performing visual and manual inspections will all change. Not all current job titles will be impacted. Tool and die makers, as well as inspectors for highly critical items that just cannot be inspected by digital means, will have minimal impact. Additionally, new job functions will be created. Others will emerge as the Industry 4.0 revolution continues. But we do know there will be a need for employees with skills in advanced manufacturing, agile, robust, integrated manufacturing, modeling and simulation, including model-based systems engineering, or using the digital thread to minimize multiple designs or prototypes or test iteration, intelligent machines, using self-aware manufacturing hardware, smart sensors and controls to develop instrumentation for legacy equipment, and use big data analytics. Advanced analysis. These are jobs in high-performance computing, designed for manufacturing, integrated smart design tools that reduce over-engineering. And finally, cyber-physical system security. These are trusted networks, gate and IT controls, or ISO 27001. The DMD revolution is going to open up even more opportunities for a skilled workforce, creating a market for higher paid workers who use their knowledge to impact the creation of the next generation of advanced products.
Okay, this particular slide will explain you as to how one should move from the traditional workforce to the more high-tech workforce who are trained. Otherwise, they will be left behind and there will be more unemployment unless we have the transition in the workforce. They must learn the high-tech. So that's what is explained in this particular slide. So there will be national and global impact. The governments have to do their role, countries and regions and cities, international security aspects, society, inequality. See, once you say transparency, how it is going to affect security, also data security and other issues are there. Society, there is again inequality and the community issues, and then individual identity, morality and ethics, human connection. So these are all protocols that to be fit in with the implementation of the digital manufacturing. See, top 10 skills to be relevant in Industry 4.0. In 2015, we have identified complex problem solving, coordinating with others, people management, critical thinking, negotiation, quality control, service orientation, judgment and decision making, active listening and creativity. Now you can see in 2020, complex problem solving remained there, but critical thinking has come to second place, creativity, people management, coordinating with others, emotional intelligence, judgment and decision making, service orientation, negotiation, and cognitive flexibility. The flexibility is the one that has added here, which is not there earlier. And then data security I have been mentioning, especially disaster recovery. Whenever something happens, how to recover the data. Suppose you are in digital manufacturing, you are see when product design changes every time, a lot of data it is generating. How to take care of that? That is explained in this particular.
Just in the context of the digital thread, think of the things that could truly bring you or your organization down to its knees. Something probably instantly came to mind. Dig deeper. That's probably not the worst thing that can happen. With 1 foot in the world of information technology and 1 foot in the world of mechanical engineering, I have a fairly unique perspective on the lessons to be learned that make the adoption of the digital thread possible. In the information technology world, there's a large focus on security and disaster recovery. There are people whose entire job it is to think of that question I just asked of you, to really think about the worst case scenarios. When I think about worst case scenarios, it generally revolves around the destruction of a location, whether that be from fire, flood, or some other disaster, it means that the place
So
from which I operate becomes complete.
Therefore, you have to see the big data will come into picture. Let me explain this because this video is taking a lot of time. So the big data comes into picture. We have to have the data backup. I mean, across the different locations in the world. So if something happens in one location, the other location, the data saved must be made use to run the system. That is what this particular slide explains. And then the vision I want to run, the vision of digital manufacturing and design is like this. Yeah, please see this. So this gives a future direction. So let me, there is a small technical issue. One moment. Give me one moment. There is a technical glitch. Yeah.
Take a moment and think
So
about
you're
a
all
friend
getting,
or colleague
is
who
it
does not
audible?
have a cell phone. In addition to feeling disconnected from the rest of the world may think of them as disconnected. People can even come to ask, how do we stay in touch? Now combine that thought with the idea of seamlessly sharing information throughout the life cycle of a complex product. Large integrating manufacturers, or OEMs, will expect that all of their suppliers use technology to increase efficiency and effectiveness. In fact, these requirements are already being incorporated into the bidding processes for contracts. Those who are not digital need not apply. This module focuses on the ideal digital manufacturing and design world, with an ever-present digital thread at its center. Some years ago, there was a Defense Department program review where one of the attendees stood up and mentioned that now that there was a requirement to use a digital technical data package, or TDP, the number of bidders dropped by 50%. That means that just based on the conditions of the contract, even if they produced a world-class product at a great price, some companies just could not compete. And that was quite a few years ago. In many areas of industry, the digital thread is well on its way to adoption. As with other advances like supply chain management and Six Sigma, once the benefits are known, others will adopt the innovations as well. Many of the components of the digital thread will be incorporated like trade secrets. Competitors will just get faster and produce better products. At the same time, companies are increasing the expectations of their employees beyond manual labor. When I say manual labor, this doesn't just include physically lifting equipment and products, it also means controlling equipment like machining centers. A reality that exists is that manual labor costs are lower outside the US, making going offshore an option to companies that look at keeping unit production costs low. Instead of lowering labor costs, an alternate approach is to increase productivity, producing more products with the same workforce, often with some form of automation. This relies on the willingness of the workforce to innovate, adapt, and take more responsibilities within the production process, both in design and in manufacturing. In the next lesson, we'll introduce.
So that is what future you have to have to replace the manual labor or the hardworking labor with the thinking labor in order to implement the digital manufacturing successfully for the enhancement of the products, particularly to bring out the products as per the customer expectations. So now I am my presentation is over. Now it is open for discussion. May I invite some of you to ask certain doubts.
Discussion we'll have at the end.
Okay, sir.
Also have our other speaker complete.
Yeah.
Then we can have the discussions at the end. Okay.
Sir.
So
Okay,
now if your presentation is over, I will invite the next speaker.
yes, sir. Yes, sir. Yes, sir.
So okay, then very nice, Chandramohan Reddy garu. You have given an elaborate and very extensive presentation on Industry 4.0. Now we have one more person with us, Dr. P. Srinivasa Rao. He is a global head at Infotech, that is Scient
Yes.
software company, and he'll be dealing now, with Industry 4.0 versus Industry 5.0. That is one thing, and also what is artificial singularity and its impact on future of our factory, and also smart manufacturing and evolution of connected factories. I request our P. Srinivasa Rao garu to start his lecture, and before that, just give a free introduction about people are going on seeing these videos, and I think a lot of information has been given. Please explain what is the difference between 4.0 and 5.0, and then start your lecture.
Sure, sir. Thank you. Hope I'm audible.
Yeah.
Okay. So first of all, I would like to thank President Dr. G. Rameshwara Garu and Principal of CBIT, Professor GPS Rama Garu, HOD Mechanical CBIT, Dr. PVR Ravindra Reddy Garu, and my Guruji, Dr. S. Sachinarayan Garu, and my guide, Dr. G. Chandramohan Reddy Garu, and the other eminent speakers like, delegates, K. Guru Brahmam Garu, T. Anjay Garu, and other delegates, faculty, students, ladies and gentlemen, warm welcome to the session. Hope you're all doing good and safe. Let me start with, as Guru says, Dr. Satyanarayana Garu and Chandramohan Reddy Garu says, there are actually, so many advancements, technological advancements, sophisticated things are happening in the entire world. They have touched upon some of the areas, and as requested or suggested, I will, elaborate. I'll start with a video, which will definitely a self-explanatory, and then I'll start giving you the details. Let me share the screen.
Once upon a time, business as usual was often good enough. No more. Where we are going, good enough is dead. In a world where everything is connected, where everything is equally excellent, where performance is reaching perfection, there's only one space left to innovate in: you. Right now, you are a central point in the raging tornado of change fueled by digitization, mobilization, augmentation, disintermediation, automation. Well, the list goes on. Science fiction is becoming science fact. Think about self-driving cars or computers that can learn and think. The way we work will never be the same. The skills we need will be dramatically different. Winning or losing are now happening faster than ever before. So what's your response? How will you discover new opportunities in one of the most transformational times in human history? Are you driving change, or are you being driven by it? Disruption has become the new normal. With change, it's always gradually, then suddenly, well, things really have stopped happening gradually. This change is exponential. Everything that used to be dumb and disconnected is now wired and intelligent. Cars, cities, ports, farms, even our bodies will be wired with sensors and will talk to each other. These game changers are also combinatorial. They amplify each other, creating a perfect storm of change. Quantum computing fuels big data. The Internet of Things fuels artificial intelligence and deep learning, which fuels robotics. However, anything that cannot be digitized or automated will become extremely valuable. Human-only traits such as creativity, imagination, intuition, emotion, and ethics will be even more important in the future, because machines are very good at simulating, but not at being. Yes, robots and software will do some of our work, but this will allow us to focus on things that cannot be automated. To imagine change squared, you've got to start engaging more with what might be, not just with what is. Immerse yourself in the immediate future, 5 to 7 years out from today. We need to go beyond technology and data to reach human insights and wisdom. Technology represents the how of change, but humans represent the why. The future is about holistic business model. The opportunity is to be liquid, to learn just in time, not just in case, not single improvements, but complete transformations, not individual systems, but new ecosystems. Humanity is where true and lasting value is created. We will engage, relate, and buy things because of the experiences they provide, because of their transformative power. The future doesn't just happen, the future gets happened. The new way to work is to embrace technology, but not to become it. The future is in technology, yet the bigger future lies in transcending it. Let's live and lead from here.
Yeah, as the video shows that all smart things, all dumb things are becoming smart. And okay, see, all fiction, science fiction. We used to have science fiction, right? It is becoming science fact. And what is going to be valuable? What is not going to be valuable? All the mundane tasks, actually repetitive tasks, are not going to be valuable. There will be a robo lawyer, robo teacher, robo doctor, robo engineer, okay, which will automate everything. Okay, but will actually this automation and robotics takes away the jobs from the job world or manufacturing world? The answer we are actually going to explore through the presentation. Yeah, let me share my presentation. I will share the entire screen so that there will not be any issues. Yeah, before we actually talk or touch upon the factory of the future or a smart manufacturing or digital manufacturing industry 5.0 or 4.0, okay, let us talk about what is happening around the world. If you are aware of what is going to be like, no, so that your preparation altogether will be different. Okay, so so most of you actually might have heard what is 3A. Right now, the world, either actually a software industry or a manufacturing industry or anything, is now ruled by 3A. So can you guess actually what is 3A? Yeah, instead of actually making this as a monologue, I want actually this session should be interactive so that people can type in or key in your answers or responses in the chat box as we proceed. Okay, so if there are no ideas, then I will move on to, so all of us, we are talking about automation, either it is a software automation or a hardware automation, okay, whatever. We have bots in the sense robots, cobots, and software bots, okay, the software application is a software bot. And then analytics, okay? Based on the automation, you will have actually so many sensors deployed, so many predictive analytics techniques are there. Then you can maintain and you can actually monitor the health of the system, okay, through this automation and analytics. And also on top of it, okay, artificial intelligence or AI is actually applied. We'll discuss in detail. Don't worry about it. So then we have even AI and IA. So can you guess what is IA? AI is obviously artificial intelligence. So what is IA? So Industry 4.0, the people have done everything automated. And there is actually, this is a dumb system of automation. So they have not actually, tried to make sense out of it. Okay. So in this case, IA in this sense, intelligent automation. How do we actually make a system self-intelligent or some bit intelligent? Okay, somewhat of. Let us go into the details. Yes. Now, I want answers from the students. What is this? This is very interesting, right? So I want from the student fraternity, what is this? What do you mean by this? What is your perception? Please type in or key in your response in the chat box. I'll be accessing the chat box. I want at least one or two. Hope I'm audible and this is visible also. So hoping that you are not sleeping. Yeah, Sujit says it is cobots. So you have to elaborate, sir. Like Hemant tried to say that robots taking up human work. Okay, good. Let us actually look at the answers. Yeah, thanks, Sujit. And yeah, Vasu again says collaborative bots and with human intervention. You are not able to guess. Okay, human machine collaboration, somebody is saying. A bit approachable, actually, right, but not really accurate. Okay, anyhow, yeah, thanks for the response. See here what happens. So your boss will have 10 people reporting to him and 10 bots reporting to him or her. So as someone said, we are going to collaborate with the machines. We are going to work together, and all are actually, going to attain legally equal status, legally and technically also. We'll discuss more in the later slides. Yeah, this is what actually I'm trying to say out of this. Okay, you have to beat the bots. How do you beat it? What kind of skill set you should possess? What kind of actually awareness, okay, on the automation, intelligence, intelligent automation, artificial intelligence or industry 5.0 technologies, the cyber physical systems, digital twin, all these things I'm going to talk about it. So as I said, 4.4 is talking about CPS, cyber physical system, that is a digital twin or virtual twin, even Chandramohan Reddy Garu has touched upon. And so what is actually 5 makes you apart from the 4? What actually distinct, okay, a distinction between this 4th and 5th? We'll have an example. Yeah, 5.0 is talking about more of human interaction. Both the man and machine has to collaborate and work together and understand, okay, everything. So yeah, particularly 5.0 is talking about society. See, we started our life with from a hunting society to industrial society, and then passed through information society, and then we are trying to create now super smart society, which is the industry 5.0 is talking about society 5.0 also. Yes. So you observe this 1, 2, 3, 4, and then 5, 6, 7 pictures, and then type in your response in the chat box. What do you mean by this? I will actually switch between this slide and that slide. So please, I'm pausing on. So 1, 2, 3, 4 snaps, and then the 5, 6, 7. What is happening here? So there is a man, okay, there is a component, there is some subassembly is going on, okay. Also, you see that pick and place robot. So he's tightening some screws or something like that. And there are components, okay, besides him. So what is actually your observation than that? These are all common things. Yeah. Please type in your response. I'll wait for a couple of responses. So after this, there won't be any questions. This is the last question I have. After that, my presentation continues. Can I seek your response, please? See, 1, 2, 3, 4, and then 5, 6, 7. Hemant says attaching some components to chassis with help of robot, collaborative assembly. See, collaborative is a fudgy word, right? Like what kind of collaboration it is happening, Suresh? Hemant, you have to elaborate what is how a robot is helping here. Okay, anyhow, as I requested, a couple of responses are there. Then I will go to the answers. See here. I'm zooming in my presentation and then see here. So there is a vision camera over here. There is a robot vision system or machine vision system or a camera installed near to the assembly station. So it is teaching, okay, the process actually has been taught to the system with the help of this vision camera, okay. So then automatically what is the next sequence? See, robots are programmed, whereas in cobots, it will actually understand, those are trainable also. Cobots are trainable. Machines are learning, okay. I have some other video, like snap after some time, but I will show you that, okay. Before that, actually, let us have what is this happening. So the cobot is reading the mind, okay, of the operator, and then it is giving the next component. What is next component in the sequence? So it has got trained, okay, but is not programmed. Please remember this. There is a difference between programming and training, okay. We are teaching. That's what actually machines are learning, okay. Yeah, there are 30 different technologies disrupting the entire world. We call it as Internet of Things, Industrial IoT, blockchain, big data. Everything is interdependent, okay, and multidisciplinary, interdisciplinary subjects. So we can't say I'm a mechanical engineer, I'm a deep generalist, okay, sorry, I'm a specialist. I can't actually be a generalist in all the technologies. So now the industry demands deep generalists than specialists, okay, most of the areas. So we have edge computing, we have cloud computing, we have quantum computing is now talking about the Google Sundar Pichai is talking about, they have achieved recently quantum computing supremacy, that is called quantum supremacy, okay. Yeah, as I said, humans are hooked with the the mobiles and all, okay, while machines are learning. This is the today's reality, okay. I'm just pulling your legs. Yeah. So before we actually touch upon the digital manufacturing, smart manufacturing, or connected factories or digital twin, let us actually talk about what is singularity, AI singularity, okay. What is singularity? Anyone have, see, not a singularity in mechanical engineering, okay? Mechanical engineering singularity is different. I'm talking about AI singularity. Why should we learn, being aerospace, aeronautical, mechanical, industrial production engineers, why should we learn what is singularity, particularly AI singularity? Okay, you'll realize after my presentation. So, yeah, evolution, Chandramohan Reddy also, sir also have touched upon the evolution. See, the transition between industrial revolution and agricultural revolution, it took 8,000 years. Okay, so it was accelerated like anything. Okay, when we talk about light bulb versus industrial revolution, and then the time has been compressed. Okay, the development time, invention time. Okay, or whatever the necessity. Okay, people say necessity is the mother of invention. Okay, but in pandemic, the necessity is the grandmother of crisis. People are seeing. Okay, necessity is the grandmother of crisis because we are in crisis. So innovation is happening like anything everywhere. You know, vaccines have developed so rapidly with our prototypes, actually rapid prototyping, and with less time or downtime, we call it as. So to the World Wide Web, it took 22 years, and to this human genome sequence, it was actually 9 years. So the time from 8,000 years to 9 years is really compressed a lot, multifold, okay, exponentially changing. So earlier the computer was of size, okay, of room size, a double bedroom sized. But nowadays, what is happening? You are talking about, okay, GPUs, which are very, very small in nature. Okay, then what is singularity in AI? When the artificial intelligence surpasses the human brain, that is the what do you call? That is the phenomena called as singularity. Okay, so who has invented this? Who has predicted this? First of all, so there is a director of engineering at Google who is Ray Kurzweil. He is known as a Nostradamus in technology. You know Nostradamus, right? Like our Veera Brahmendra Swami, like in Telugu states. So the Ray Kurzweil, his predictions are 86% accuracy, and he made 147 predictions, and then 86% was correct. Okay, or they have claimed, and it is happening. As I said, Hollywood directors used to picturize so many things. Now we are making actually as fact. All science fiction is becoming science fact. All dumb things are becoming smart. You can argue with your automobile while you travel from your office to home. You can debate, okay, what political system, what G7 is doing, okay, how China is actually, threatening the world, okay, what is actually, good and bad in India, okay. So you can argue, you can debate with the automobile. The automobile is becoming smart nowadays. We have so many things. We have connected cars. Okay, Tesla is what you call talking about autonomous cars, autopilot, so many things. And no longer you will find differential engine, that this and all in the automobile. You will only see in the museums. You are going to experience electronics, electrical, computer science subject as automobile. Okay, automobile have a subject of them. No longer it's a mechanical or what do you call automobile subject. Okay, while you have a cup of coffee in the coffee shop, your engine is just replaced. The modular assemblies are there. Okay, many of your manufacturing engineers will appreciate what is modular manufacturing. So there is a university called Singularity University in California. Okay, all futurists, future technologists are getting trained, okay, in this university. Okay, top level CEOs and CTOs, Chief Technology Officers, are taking the course actually over here. You actually visit their website and get to know many things. I'm just trying to give you the introduction to Singularity. I'm not going to talk about okay in detail. So here you can see that the Singularity is going to revolutionize the entire world till 2099. Till 2099. So 2049, 2045, what happens? AI surpasses human beings and is called Singularity. And then with that revolution, what is going to happen? Okay, and 5G evolution and robo surgeries. Okay, many things are going to happen, and the latency is very minimal. Okay, and you have human you can with the blink of your eye, you can download, upload information to the internet. These are all concepts now are going to becoming facts very soon. Okay, we only see in the Hollywood movies. Okay, but it is becoming now facts. How come actually this is possible ever? No. So our hard disk was used to actually what do you call, carry like this. We used to shift like this. 5 MB hard disk. Now you have okay, on your on the tip of your finger, you have 1 TB. Have you ever imagined the size of that? Is actually diminishing like anything day by day. So if you are an electronic engineer or a computer science engineer, you know what is Moore's law. Who actually was a co-founder of Intel? Okay, he did. He has actually proposed a Moore's law. Okay, the number of transistors on a microchip double every 18 months to 2 years, keeping the cost either constant or half of it. So that means the infrastructure is developed like anything, multi-folded, but at cheaper. Okay. So earlier the 5 MB hard disk was very costly. Now 1 TB is nothing when compared with the 5 MB hard disk in 1956. Okay. So this was actually, this is a very famous law, Moore's law. Okay. This has created actually a ripple effect in what you call both in electronics and computer science world. So you can see here. In 1971, it was 10 micrometers, and now we are talking about 5 nanometers, 3 nanometers. Okay, so it's like anything, hundreds of thousands of times. Yeah. Now touch upon actually Industry 4.0 or 5.0, the factory of the future. While we are struggling to understand what is Industry 4.0, Industry 5.0 is spearheading. Okay, it's actually with a rocket speed. It is at the speed of the rocket. It is intruding into the technology, particularly manufacturing industry. Yes, even Chandramohan Reddy sir has discussed about evolution and revolution. So what is the difference between evolution versus revolution? Like a step-by-step, what do you call, progress is called evolution. With a radical change is a sudden and radical change. Okay, basically fundamentals are changed like anything is a revolution. With an example, okay. So we used to have a landline phone. Okay, now we have a smart internet phone. This is actually the difference between evolution and revolution. Okay, so you have many examples for this, but this is simplified for this sake of benefit of audience. Yes. So intelligence are 3 types: 1, assisted, augmented, autonomous. Assisted in the sense we used to have typewriters in our what do you call office. So you can type only a certain number of copies. Okay, if you want to type, you need to again you want to make another copy. You have to retype. Okay, you can't edit so easily. But now electronic data processing is happening. You can edit, archive, retrieve. Okay, many things you can do, and you can take copies of it. So what happened actually, in the case of augmented intelligence? A washing machine, it has got a cold cycle, hot cycle, water in, water out, valve in, valve out, okay, or open, close. All this is actually with some PLC or some kind of limited firmware, okay, loaded into the hardware and then embedded, okay, embedded into the washing machine. Nowadays, the air conditioners or all the things, when IoT actually has evolved, all things are becoming smart. So there is some element or chip or whatever you call it as is embedded in, and some limited intelligence, okay, and then enhance the performance of the product or features of the product. Autonomous, the beautiful example is autonomous cars, okay, like Tesla, Google, Uber, so many people are working on this. Yes. So as I suggested, what makes 4.0 and 5.0? Most of the times we talk about cyber physical systems. I will give you more clarity on cyber physical system. What is digital twin? How GE has implemented this cyber physical system. Okay, I'll be discussing on that. So, and then now, yeah. So let me know if audio is not actually audible. Okay, please help me. pause and everywhere I'll pause and give you the details, how it is working, it's functioning. Please pay attention to this. So Predix is a GE platform, okay, GE developed by GE.
Operator, a change in my mission is causing damage to my HP turbine rotor.
Okay, Twin, help me understand the problem. What's your operating profile?
In past 6 months, my number of cold starts is 4, my number of warm starts is 8, my number of hot starts is 39. The number of start-stop cycles has increased by 27.5%.
Okay. Twin, tell me about your rotor damage.
My damage rate has increased by 4.0 times over last 6 months. If this continues, I would lose 69.9% of my useful life.
Twin, give me options for mitigating that rotor damage.
Based on weather forecasts, historical data, fuel cost, electricity pricing in my present condition, I have 2 options for you to optimize operations. Option 1 is to manually slow down my startup ramp rate so that you can reduce the wear on my rotor. Option 2 is to download the OpFlex app and apply stress controls to minimize wear and reduce fuel consumption too.
Twin, give me the factors you use to calculate option 2.
I used my past 15 years of historical data, fleet learning from 125 other D11 steam turbines like me, and 58,965 simulation runs to get this recommendation. I'm 95% confident of my assumptions.
Twin, I need a financial perspective. Tell me about the numbers.
The numbers look good. We can reduce stress by 25%, which brings the damage rate back to normal range. Startup fuel cost will go down by 40% and startup time will be cut by 50%. You will also avoid $12 million by preventing an unplanned outage.
Twin, okay, I select option 2. Let's do it.
See, based on the historical data for some years of experience, there are some steam turbines or gas turbines, whatever you install somewhere, and then you take the data and you analyze and apply algorithms, which are called machine learning, deep learning, artificial intelligence. Basically, here machine learning algorithm has been used for GE Predix platform. Okay, how do you get the data from the installations? You have actually sensors developed nowadays like anything, and mount these sensors on the equipment. I'll give you the more pictures actually as we go. Okay. Yeah, this is this particular algorithm works like a CEO of the company, and it is telling you where to stop, when to stop, what not to do, what to do. That's the beauty of this particular algorithm. Okay, as we progress, I will discuss more.
I'm initiating option 2, which is flex start. Thank you.
Okay, good morning. What you saw just now was not a glimpse into the future. This is happening now, today. This is a representation of a D11 steam turbine that's currently running in Southern California. We call these representations digital twins. What you saw was an example of the human mind working with the mind of our machines. What's a digital twin? It's a living model that drives a business outcome. So this model gets data, gets operational data and environmental data, and constantly updates itself. It also can reach into the fleet, the 125 D11 turbines, and it acquires knowledge from them and learning from them, and it incorporates this into the model. And it uses this to drive business outcomes. It can drive outcomes like it can predict, or it can warn us and then predict failures to reduce maintenance cost and unplanned outages. It can give us the ability to optimize or provide mitigation events when we find out that we have these type of failures. And it can also allow us to forecast opportunities and actually benefit from these opportunities. So let me step back and actually walk you through what occurred in this digital twin in a very simplified way. So when you think about the twin, it really operates in 3 stages: see, think, and do. So in the seeing stage, and I'll relate.
Hope you are able to see my screen over here. See, the digital twin or the virtual twin, people call it as. Okay. So the physical system is somewhere in Singapore and digital system is somewhere in Hyderabad. Okay. Consider this. And physical system is a aero turbine or engine or something like that. Okay. An equipment. So you mount the sensors over here. I'll just take the pointer. Yeah. So sensors actually you need to monitor either pressure, temperature, whatever you would like to know the parameter, which is important or significant, makes sense. So that particular sensors are generating data, every minute, every second. You can actually at regular intervals you can set up, and that data is transferred from a physical system to the digital system through cloud. If there is, for example, if you want to take a decision over here within the Singapore university, Singapore facility, then you need edge computing. So you have to install some computing device here, which is called edge computing. That means on the on-site, on the particular machine on-site, we call it as. Okay. So if you are actually sending the data to cloud and then you observe monitor the health of this system, is cloud computing. So we have now sensors, and sensors actually makes IoT. Okay, it sends the data through either edge computing device or cloud data, and then when you are transferring data from Singapore to Hyderabad, very like for example, you think that this is a nuclear equipment. Okay, in that case, no hijacker actually should actually be able to access. In that case, what you say is cyber security comes into picture. So whatever the technologies that I'm talking, all are making 4.0 or 5.0. And these are not the subjects of computer science. These are the subjects of everyone. We should be aware of it. We should be relevant. Our the skill set should be in a different way. Okay. So then the data goes to the digital system. You analyze here, and then the insights. For example, you want to change the gear, change the oil, change the equipment, or go for a predictive maintenance, or go for preventive maintenance, or go for breakdown maintenance, whatever the kind of things you want to take action, the actionable insights. The analytics gives you the actionable insights. As I said, we have 3 things, 3A, automation, okay, AI, and analytics. All are here. We have automated the data generation and sending the data to some remote area, and then consolidating, aggregating, and having after that you are analyzing with the machine learning algorithms or whatever the algorithms, and then you are taking the analytics. Okay, this is the beauty of cyber physical system. You have one physical system, you have one digital system, and the data has been transferred from one system to other system, and you are going to act on it. Okay. Similarly, the automobile. You think automobile actually is what's called dynamic component. Okay. So it's actually not stationary like a machine. Okay. So it gives you the data and sends through 5G technologies. Now 4G is not really capable of it. Through 5G technology, it gives you the data to cloud, and you can monitor the health of the engine of the automobile. And if there is an accident 10 cars ahead, it will give you the early warning system, early detection system, or alternate route it will give you. That is the power of the autonomous vehicles nowadays. And that is actually called as connected cars, V2V, V2X. vehicle to anything, okay, vehicle to a pedestrian, vehicle to any ditch on the road, a vehicle to a passenger, or vehicle to another car, okay. That's a different story. I'm not really not interested to talk about it now because it's out of it's a tangential to the talk now. So this is what actually happening. That's what actually he's talking, particularly the
Get this to what you saw previously. In the seeing stage, what it's doing, it's actually gathering data of its situation to give you a warning or prediction.
yeah, basically predictive analytics. Predictive analytics will save your time, will save your life, will save you everything. Instead of having a breakdown maintenance, okay. Even nowadays, preventive maintenance is also not really a correct or apt for companies. It's a predictive maintenance. We should predict when the system will fail with an accurate data. It all basically extrapolation and interpolation of the data.
This data that comes in is both operational data and environmental data. Operational.
Yes. So data is a new oil, A is a new electricity, okay. IoT is a new nervous system. It is very easy to remember if you actually relate to our body. What do you call it as anatomy? Okay. So A is data is a new oil, okay, a new fuel or whatever you call it as, and then A is a new electricity, and then IoT is a new nervous system. If you have data, you can play with it. Again, data makes it should be actually a sensible data, okay, structured data, unstructured data, okay, and we train the system through supervised, unsupervised learning systems, and controllable, uncontrollable aspects, anomalies can be detected, and then you can take actions based on the data available. That is the beauty of data, having data. So how do you generate data? By connecting all the systems, things to things, things to people, people to people, okay, and all those things are connected. You know, Facebook is now connecting people to people. IoT is connecting things to things, and people and things, which Industry 5.0 is talking about neural links. Elon Musk is working on neural links. Okay, a chip will be introduced into your brain, and then it will try to read the commands, and it will take the command, obey the commands, follow the commands. Okay, and it will give you the health of the brain, health of the things also. So there is so much of happening because of singularity. Okay, that's the beauty. Please be aware of this.
Data like the steam temperatures, the bowl temperatures, the rotor speeds. It takes that data in and it uses a model, that living model. This is a hybrid model of physical and digital capabilities. So it's a combination of metal fatigue, metal creep, Bayesian learning, and other machine learning techniques. And it uses this to create a cumulative damage understanding of what's happening on that rotor. As it does that, when it hits a threshold, it can then warn us there's a problem. It then can actually predict the problem. It also uses similarity learning techniques to reach into that fleet of 125 other D11s and gather their knowledge as well. So this is a model that's constantly updating itself to reflect the precise conditions of the asset and then learning from others in the fleet. After it does that, it has the ability.
Once you develop the model, it will start training itself. Okay, so no human intervention. It's only data generates and data flows. Data actually accumulates, and the sensible data is sanitized and then taken into the system, and it starts predicting the happenings.
Ability to give us these insights at the right time. That's the first stage. And it does that through APM and using the digital thread to get all that.
Yeah, he talks about digital thread. What is now a digital thread? Here. So earlier, there was no communication between top floor and shop floor. Top floor in the sense CEOs, decision makers sits. Shop floor in the sense is the production process, production takes place. So there is no communication, from the shop floor to the top floor. That means always unidirectional. It's not bidirectional. Okay, so CEO takes a decision and production follows some process. Okay, but can a production process or the shop floor influence the decisions of top floor? So Industry 4.2 or 5.2 is talking about the bidirectional communication. So from engineering department to the warehouse, there is a digital thread. Everywhere data is generated and data is recorded and data is analyzed and decisions are taken. Okay, there is, see, again, you can say that actually, no, we will lose the jobs by automating this. No, you are not actually, what you call, taking away the jobs. The aggregators, the routine tasks, repetitive tasks, who actually performs, those people's job will be eliminated. But there will be a job created at the higher level, need some intelligence, need some knowledge, need different kind of skill set. So in the lower plane, you are removing the jobs. In the higher plane, you are creating. The only thing is the IQ levels or EQ levels or digital cues, digital quotient levels have to be different. Okay, jobs are there, and it takes away the 50%. The automation and robotics or any automation, either software or hardware, anything takes away 50% of jobs and creates 70% of jobs in the other plane, in the other field. But only thing, provided you have different kind of skill set, different kind of intelligence, different kind of access to the information. Access to the information makes you great. So the CEO, particularly in aerospace environment, the what do you call, the production will have so many facilities. Okay, so many, so much of inventory lying over there. We never know that particular part is lying for 10 years or 2 years or 2 days. Okay, many times, because it's a very huge inventory, huge factory, it's not so easy to trace. Nowadays, what is happening? RFID tag has been attached to each component, either sub-assembly or assembly or something, or component level, and CEO or a production process engineer walks across the shop floor. He will get notified what is happening, whether the system right to him is working, left to him is not working. Okay, is it operational or actually inoperative, or okay, need some maintenance, or this is lying for 10 years untouched. Such decisions can be taken only with the help of a cheaper RFID tag and the IoT instrument that you carry. You carry a mobile phone, walk across the shop floor, and it will tell you in the matrix form, row number 2, column number 1 component is not actually touched for 10 years. Such kind of dead inventory. Okay, you can make actually productive things. No, you can make things productive. These are all connected. So I'm talking about if factories are connected, components are connected. So when you talk about how things are connected. Yes. So the components are smart, the machines are smart, even the bin is smart. The bin that carries the component is smart. It will not allow you to place a wrong component in the right bin. It will talk to you, it will interact with you, it will tell you that this is the process to assemble or disassemble and keep actually in the bin. The smart bins are there. And again, the cost is not really great. The cost is really manageable. And the saving that you actually get out of this system for over a period of time is actually very high than the initial investment. You may see that initial investment is very high. No, it is true. Okay, but in the case of like the dividend or the fruits that you enjoy after implementation is definitely cheaper than anything else. Yeah, the digital twins, a city can be connected and maintained through digital twin. A factory can be done. A highway, a connected vehicle. I was actually talking about the vehicles. Okay, buildings, grid. Everything can be made as digital twin. A process, a system, a component, anything can be made as a digital twin. That is the beauty of cyber physical systems. Okay. So traditionally, what happens? You develop and then plan and then deliver and have a support. This is a traditional supply chain. Whereas in the digital supply chain, I'll tell you a beautiful example. A salesperson, okay, in the sales field have just actually ordered 100 components. The moment he will have a tab, okay, a palm top or a mobile, whatever the device you have been actually, he has been given, you will enter that 100 components to be delivered by 25th June. The moment he locks in, then automatically the system will send you the mails to these raw material suppliers, vendors, and shop floor to maintain the surge or the what do you call it as the supply, okay, uninterrupted supply of components to make 100 delivered on 25th June. So a salesperson is dictating what to do in the factory. This is possible only with the digital manufacturing or smart manufacturing or connected factories customers. So earlier in the traditional supply chain, okay, you deliver, okay, God knows when you will deliver, okay, because the lead time for M10 into 1.5 bolt, which comes actually from Japan, takes 28 days, and it will decide the future of, okay, the supply. A small bolt is just defining or deciding or dictating the supply. But whereas in this case, based on the lead time, the SAP system or ERP system sends the okay, and it is just in case again the inventory when inventory is coming down to the dead level or set level, it will send you the mail automatically. There is no human intervention. The purchase guy will actually send a request to the supplier, and supplier sends it. It's not like that. A mail will be shooted or dropped to the supplier within no time, the moment that inventory or the moment sales guy locks in the order. I will pause on and I will take a couple of questions intermediately. Otherwise, I'm thinking actually this is a monologue and you may actually end up in sleeping. Anything you want to know from this presentation? A couple of okay, questions from the chat I would like to encourage.
Srinivas Rao,
yes, sir.
We'll have the questions at the end because no, even.
Okay, sir. Okay, sir. Thank you, sir. I will do that.
So if you have finished it, then I will request, our guest to
okay,
give
sir.
demonstration.
Can I take 10 minutes or am I allowed?
You take, time is there.
Okay, sir. Please let me know when to stop also. I'll take 10 more minutes.
So you can, 12:30 you can close.
Okay, sir. Okay.
12:20.
Fine, sir. So generally, how do we start the the transition from a traditional factory to the connected factory? You first have to integrate yourself within the factory, and then okay, this particular vertical integration, I will just take the presentation, the pointer. So here, say that this is in Hyderabad and this is in Germany and somewhere actually, okay. And this you have to vertically integrate yourself within the Hyderabad facility and within the Germany facility, and then start integrating this with a horizontal integration. Okay, so here you have intelligence everywhere. But wherever or whenever there is a data, the intelligence is available. Okay, yeah, we will continue with the video for Guy and
data. The second stage is the think stage. Terrell described in the cloud on those.
I'll move on because no time. I'll move on and then give you the highlights.
What you could do, load it to the edge, ramp. That's what it means, creating these capabilities. The problem.
This is the Microsoft HoloLens, and this is a AR, VR, XR, MR. We have augmented reality, virtual reality, extended reality, okay, mixed reality. This is a mixed reality component. This is a Microsoft HoloLens, $3,000 of worth, and it will show you what happens, okay, because the presenter or the speaker is somewhere and the installation is somewhere 600 miles, 800 miles away.
How about I use one of these Microsoft HoloLens, which I suddenly actually
he will bring that particular
and what I would do there is I would on the physical asset. What I'll do is and simulate it in this environment.
It is now in the audience. Virtual component.
Right? Pairing twin. Okay, that did. Okay, twin. Show me.
So the machine learning algorithm says that there is a damage. Okay, so he is trying to analyze where is the damage, because you can't open and see the things because it is a large installation. It takes months together to do something.
Where the where is.
It will also show you the plot.
A baseline for me so I can see if we did no mitigation, what that would be.
So the machine learning algorithm, like thinking like a CEO and saying that why do you want to produce electricity at this rate? Let us optimize and save the life of the rotor for some more time, because the electric tariff in US is now coming down and you will not make any profit. So it is actually giving you the entire scenario. Okay, it's a Mr. Dependable. Okay. So let us see now how things are actually, how cobots are working nowadays. See here a man passing actually across, and then what is happening? So it will stop and proceed. This is a simple phenomena. So it will take decisions if there is a interference, okay, a man passing across, then it will take its own decision, okay. These are all cobots. Nowadays, cobots are also trying to, understand the emotions of, operators. If operator is distressed, if operator is very energetic, okay, it is actually mood-based engineering. That's a beautiful subject. This is very important.
Sandvik Coromant has been in the forefront in the metal cutting industry for more than 70 years. What we can offer for our customers is specific knowledge at the tooling level, minimizing idle time up to 50%. At Sandvik,
so in the vertical inserts, inserts actually failure or wear and tear inserts will actually lead to less production and damage to something, right? So all the inserts are smart inserts, and pressure, vibration, temperature, it reads and gives you the data. And based on that, actually, you can prevent the breakdown, you can prevent the damage to the component or the tool or machine.
At Coromant, we use Azure IoT Suite to collect data in real time and getting facts out of the machining process. With our sensor-equipped tools, that is possible. If you know the temperature, if you know the load, if you know the vibration, if you have that and can use that type of data, you can increase the efficiency of the machining process and generating savings for our customers of millions of dollars.
Yes. This is because of the infrastructure, the computing infrastructure available at cheaper rate, faster, quicker than earlier stuff. That's number one. Number two, the sensors are actually evolved and developed like anything, and it's available at affordable cost.
Our decades of knowledge and experience from the metal cutting industry combined with Cortana intelligence, I think makes the perfect blend. It is about using the cloud, giving instant recommendations.
So you use data, you use IoT, you use cloud computing, everything. See, all are inseparable, all are dependent, interdependent, superimposed, okay, and penetrated into one another.
About cutting parameters, speeds and feeds, connect that to our CRM system, bring that into our call centers and instantly give feedback to the customer. This enables customers to predict when to change a tool, when to order a tool, how to move out of a vibration zone. In simple words, how to become more efficient.
Yeah, based on the lead time, it will actually order the component, okay. So what is happening at Scient?
Up at Scient, then you bound your assembly.
Need for a software that manages them seamlessly and adapts as per the requirement. Scient's one immersive platform addresses all AR, VR devices. Software helps in collaboration between several people in real time.
So it's Microsoft Hololens, and they are using, and then they are trying to explain, one engineer is trying to explain to other engineer, or they are discussing about the experience. This is a collaboration, we call it as. This is possible only with AR, VR, XR, MR kind of applications or the tools.
The VR training app delivers. You can save your progress at any given convenience. Profile and
this is here. So this is an aero engine, and we have an issue, and expert from Germany, is explaining a layman or a very unskilled labor, you can see, or a limited knowledge this particular operator has, and they are actually training or guiding. Also, it is highlighting the right component to measure and give the data.
Voice and object recognition engines power the remote assist.
So it's a remote, even telemedicine nowadays in medical field, telemedicine expert sits in London and then he is operating, a patient in Hyderabad. And don't get surprised, a robo surgery, being a mechanical engineer, or a robotics engineer, you appreciate how this is operated and not to scare.
In troubleshooting any maintenance problems, removing the constraints of time and distance.
In Scient, so that is the beauty of that. And now
welcome to the smart connected factory of the future. Here, man and machine come together and utilize data to drive more efficient and profitable manufacturing processes than ever before. There's a huge range of modern technology deployed across the factory, all designed to improve interactions between people and.
So imagine we are using all these technologies, you call it as VR, AR, IoT, artificial intelligence, robotic process automation, cybersecurity, cloud computing, edge computing, and quantum mechanics. Nowadays it is evolving. All these things are applicable or applied into the manufacturing, into the connected factory, into the smart manufacturing or digital manufacturing, whatever you call it as. And 5G network, the development of 5G network, how it is helping the manufacturing industry. You try to explore these kind of things. The latency is less than 2 milliseconds. The speed at which we are actually going to achieve with the advancement of technology is different. And AI-based diagnostics, the machine vision system or robotic process automation. For example, in a bolt manufacturing industry, the bolts are manufactured at a faster rate, like 1,000 per minute or 100 per minute. How do we actually, segregate bad versus good? So the artificial intelligence enabled image analytics software is deployed, and it will show you the bad and good and sort it. Earlier, we used to sort with automation. It is now with the help of vision. That is the advancement. What is happening? So this is called machine vision system or robotic vision system. And then no longer the car is actually going to be seen. The automobile that you are seeing now only can be seen in museums. So all are electrical, electronics, computer science subjects or getting introduced into the automobile. So as I said, autonomous electrical vehicles, and another beauty of 3D printing. You visit a garage and tell them that there is a problem in the automobile. He will check and diagnose and locate that this component ABC has to be replaced. The garage, usually if you think that it is a BMW, okay, and he will say, sir, this component I have to either bring from Germany, or easiest thing is Singapore, which is the hub of so many things. So it will take 1 week to 10 days, and you may have to come after 10 days. And your automobile is down till that time. So what do you, with the introduction of 3D printing, and even nowadays 4D printing is also there. The fourth dimension is the time. Okay, 3D printing with the help of additive manufacturing technique, you just tell them the part number. He will print that part by the time you have a coffee in the coffee shop opposite to the garage. You just have to see, when the International Space Station asked the ground station, please send a spanner, please send a screwdriver, please send that bolt, this bolt, you know, sending from ground station to the International Space Station, it will not happen every day. It will take its own schedule. So the operations in the International Space Station will stop. Then instead of that, what this ground station scientist said, Are bhai, I am sending a additive manufacturing, what you call 3D printer. You print whatever you want. We'll send you the 3D models from the ground station. That is the beauty of 3D printing. So how you can use the 3D printing was talking about 1950s, and still it is gaining popularity. It still is not in really, okay. But our, like, no, in the home, like in the office, you have a 3D laser printer, ordinary laser printers, right? Like that, you will have a 3D printers in the house. You can yourself print the part and replace. That's going to come, okay? But it takes time. Somehow the cost is not coming down in case of 3D printers. Yeah, so the drones delivering a package at your doorstep, the supply chain management, particularly, which is the backbone of your factory. Okay, a drone lifts some products from your workshop to the customer. It is capable of. Yeah, a connected factory generally uses sensors and cloud-based storage and analytics. As I said, 3A: automation, analytics, artificial intelligence. So data flows from shop floor to top floor to shop floor, and the shop floor people are can influence the CEO, okay, with the details. That's the beauty of it. Yeah. Let us continue this, and then
systems. Designers can innovate in modern creative space, and assembly teams can train digitally using virtual and augmented reality. Collaborative robots enable workers to get hands-on with complex and cumbersome parts of the production process. Teams can continuously monitor every tool, process, and part deployed in the factory, thanks to the Internet of Things. That data is automatically turned into actionable insight using artificial intelligence. AI can even perform complex problem-solving analysis and identify root causes in a nick of time by bootstrapping data and performing virtual experiments to validate them. Together, all of these technologies help drive leaner, more cost-effective operations, cut time to market, and enable continuous operational improvement. But even the most powerful technologies need the right support and the right people behind them. The smart connected factory of the future depends on two more essential parts: a team of driven innovators with the right digital skills, and a streamlined, standardized data foundation that enables every piece of technology to interact seamlessly and learn from one another.
Yeah, in the warehouse, you will able to see something like this in the warehouse. See here. So with this lens, very okay, cheaper and affordable lens. Okay, not really Microsoft Hololens $3,000. This is an interactive lens, and the component, whatever the smart glass, with the help of smart glass, you can read the life of this, okay, the shelf life of this, and when it is manufactured, and which factory, which location, okay, why this is lying here in the warehouse, because warehouse is a very big facility. It's not so easy. Amazon warehouse, if you see, you will wonder all are operated with the help of cobots and robots. Okay, auto guided vehicles. Okay, automated guided vehicles, AGVs. Okay, and yeah. So one last thing I will actually talk about some digital interaction. Sorry. Earlier, we used to have manual interaction, manual work instruction sheets. But now, digital instruction sheets are there. It will guide you, okay, how to it's called assemble or component, how to assemble a component. I'm checking for that.
Tomorrow's factory parts are complex designs that require skill and dexterity to assemble.
With this, I will stop my presentation. This is the, I think, the video that I'm talking about or referring to.
This means no robot can compete with our operators. Our vision of digital manufacturing combines human skills and experience with smart tools and big data, helping to maintain Megit's edge in the face of global competition. Megit Modular Modifiable Manufacturing exploits intelligent, data-based systems to support and upskill our operators while allowing them to focus on core assembly activities. Welcome to the M4 Lab.
So this is the assembly bench.
In our demonstration laboratory, we can follow components as they are kitted, transported and assembled. The journey starts with the smart kitting station. First, the operator collects all the components that are needed. Laser feedback systems mean that only the correct...
So laser is saying, sir, here it is showing red. That means you don't pick this and you have to pick this. This is with the help of a green light. Laser guided.
Items are selected and mistakes are eliminated.
The RFID reader, he is reading and then putting in a smart bin and for assembly.
Each component is tracked individually, ensuring complete traceability, essential for
data is fed because of while scanning that you are feeding the data.
Aerospace. Detailed on-screen instructions keep the process smooth and simple.
Yeah, the bin will accept only the right component.
The complete kit is secured inside a smart box, where environmental conditions are actively monitored during assembly. Computer vision is used to verify the kit is ready for dispatch, and the smart box is collected.
Yeah, with the help of computer vision, like ideal layout and what is now placed. So previous wireless versus recent. It will compare the image and it will tell you that there is some component wrongly placed. Even in the assembly of PCBs are very minute components, right? So even there we are using image analytics. Our what do you call facilities near to the GMR airport, Aerosage.
By delivery robots. These robots use sophisticated algorithms to intelligently plan their route and deliver components just in time. Smart boxes and tools are tracked by an indoor location system, which not only prevents misplacement, but also dramatically increases the transparency of the factory. Our closed-loop adaptive assembly workbench, CLAW, can be rapidly reconfigured to work on many different products. CLAW recognizes which components have arrived and prepares everything required for the specific assembly. Once the operator is ready to begin, CLAW adjusts the workbench to the operator's preferred height and light level before loading up detailed digital work instructions.
Yeah, this is what digital work instructions. Earlier we used to print and then place near to the worker and assembly bench, right? The operator follows, okay, reads and follows. Now this will guide you like anything. You just see this assembly.
These instructions are twinned to the orientation of the product and are animated to show the next step.
Guide you step by step, what to fix, what not to fix.
Lasers and computer vision guide the operator through all stages of
The green light is guiding to pick the right component.
The assembly, and
In the assembly process,
smart tools automatically torque fasteners to the correct
the
value.
moment he picks that particular component, the torque wrench has been set for the correct torque.
Throughout the assembly process, operations are verified by the smart bench. Upon completion, built-in weighing scales ensure all components are present and correct. Feedback and ideas to improve any process can be submitted directly by any operator at any time.
So there is a communication between one operator and another operator. The knowledge that one operator has gained, either a failure or a success, can be shared to the other operators. This is a knowledge management or collaborative learning. This is possible only through the smart bench. Otherwise, what we have to do is some operator will start document the things, and the other operator has to refer, which there will be a confusion because always but this is really visual. What you visualize is easy to memorize. So that is the beauty of visualization.
Continuous improvement suggestions can now be traced right to the source. Feeding data into a digital twin allows decisions to be trialed in the virtual world before any material is cut.
Yeah, with this, I think I'm done. So there are many other things, but basically, we want to be part of this. So India is struggling at $412 billion, particularly in the manufacturing space. How do we compete with China, Germany, US? A long way to go. And so this is the picture. I have visited the digital transformation factory at Siemens Mumbai. Everything is connected. Whatever now we are talking about is there physically, practically. I have touched, felt, sensed, everything. So that's the reason I can actually share my knowledge lively. Otherwise, it will be theoretical. Thanks a lot. Thanks for the opportunity. How to close this? Not to share.
Thank you, Srinu. You have given a wonderful presentation. And
Thank you, sir.
a lot of, when you touch that on, a lot of new things. Like, you were telling that about SMEs are about 95% in America, and 94% people are, utilizing these digital factory technologies. It's wonderful, The same thing comes to India, we'll be doing wonders. And we can almost equal to China once the digital technology is implemented in India also. And also, digital twins you explained with a very good simulation. Like, talking to rotor and finding out particularly the practical experience, like steam turbine GE D11. And it's, damaged, why it is damaged, and what is the solutions required for correcting the damage, and what the cost that is going to, incur for damaging this. So all the things are, really very, very interesting for the people like me. And now one more thing is also touching about 4D printing. It's a great thing. Now we only talk about 3D printing. Now 4D printing, that is the time dimension is also added and has become 4D printing. Thank you very much. Now we have one more last and final demonstration with us. We have one Mr. Soras Vaishnav, Senior Application Engineer. He works for India Soft Technologies Private Limited, Pune. And this company is founded in 1993, and they have been supplying various types of simulation softwares to various engineering colleges and organizations. And Mr. Soras has a diversified knowledge, and he is expert in particularly softwares like Witness. That is a simulation tool for digital manufacturing, SIM, FMS, and factory automation. And also he is a Pro Simulator, that is power plant simulation software, and Automation Studio for hydraulic, pneumatic, and other simulation purposes. And he has been addressing various people and participating in various seminars. And now I request Mr. Soras to take over this session and give us some demonstrations on various simulations.
How much time, sir?
Maybe about 15 minutes.
Okay.
Good afternoon, everyone. Thank you, sir, for my introduction. So I hope I'm audible to you.
Yeah, yeah.
So I'll go ahead. So you can see the screen now. I'm going to present you a simulation.
We are able to see that.
Sorry, sir?
We are able to see your screen.
Yeah, okay, good. Then I'll go ahead. So today the topic which I'm going to present is a witness simulation software. Srinivasan sir has given a very good presentation about digital twin, and he has given a good insight related to that. Now I'm going to showcase you a simulation tool which is a predictive simulation software. Using a digital twin, we are going to do a prediction of the manufacturing plant. So this simulation software, it is called as a discrete event simulation software for predictive simulation. So Witness Horizon is it is developed by a company which is a UK-based company, Lanner Group Limited. In 1996, they had developed that. That is the first kind of tool in that area which has a very flexibility to model a simulation models in the environment. Like we have a drag and drop facility, and very easily you can model this type of simulation model of a digital factory. So as I said, it is a discrete event modeling and simulation. I wanted to show some PPT related to organization and solutions we give to the engineering institution. Before that, I'll directly go to the tool. Then in the last, we'll discuss on the PPT for some minutes. So instead of going to the PPT, I'll directly move to the tool first, so you'll get the idea. I have a limited time of 15 to 20 minutes. I'll try to complete that in that time. So you can see in screen, there is one image. You will be able to see that it is a 3D image of a factory. And what we are going to do, we are going to model a simulation model of a factory in the virtual environment, and then we can convert that model into 3D also. Why this type of simulation tools are used? First, let me show you one job application from the Ford, which is Ford their global business service center, which is in the Chennai. So basically they do their R&D work in that area. So they are a user of a witness simulation software, and this was a job requirement for that. A simulation engineer they required. This was a last year job requirement. Simulation model building analysis using discrete event simulation tool. Then responsible to deliver various program of simulations. Okay, deliver validation, bottleneck analysis, material flow simulation. So this type of simulation that person has to perform. Why this type of simulation softwares are used? First thing. Now, day by day, you can see there's a huge change in the, you can say, a manufacturing pattern. Day by day, you will able to see a lot of different models are coming. I take an example of a cell phone industry, mobile industry. So like, for example, you can see each and every company launch new model in each and every week. So you get a different model with a different specification. So for balancing their plant according to the new requirement, according to the new product, according to the new production throughput requirement, they have to change the plant at the actual level. For changing that plant, for change management, we require a validation for that. So for that validation, we have a simulation tool like a Witness. So you can see my screen, the Witness environment I have opened just now. So in the screen, you will be able to see at the bottom side, I have added an element. We have given elements like a designer elements. You have a part, material, machine. So we require a man, machine, material. So this is a labor as in the form of man. Then you have a machine. Then you have a part as in the form of a material. So you use these type of elements to model your factory and to predict something, to do a changes in the virtual environment, and then go for the actual changes on the field. So before going to the actual changes on the field, we use a simulation tool, a predictive simulation tool like a Witness. And in that, not only this man, machine, material, we require a material handling system also. So you'll have in the transport section conveyor, then parts, then you will have automated guided vehicles, then tracks. For building a gantry systems, you have a various types of overhead sections and carriers. You can have in a chemical industry, you might have a liquid tank processor. Then you can require various types of machines, say CNC, lathe, all those machines you can insert in the environment. Here we are morely focusing on the process. We are doing a copy, we are doing a digital twin of a factory to get the future prediction here, to get the future, what is the projection of my factory, what will be the throughput of my factory, or what are the optimization I can do in my factory. So basically in the digital twin, basically we are not only replicating that factory in the virtual environment. With that replication, you are doing a simulation and you are going to do a projection as well as optimization in the simulation environment. For example, I'm going to roughly build a small model. Like I have a factory, instead of factory, I'll say a workshop where I have two machines, two conveyors and part. So for example, I have to just drag and drop all the elements. A part I've taken a machine, then I go to the conveyor. So I take a conveyor. Similarly, I'll add one more machine. Okay, I've added one more machine. Then after that, I'm going to add one more conveyor. I'll zoom that out so you'll get a good idea, good view. Yeah, okay. So now you have conveyor, then you have a machine. Then I'm going to add one more conveyor in that environment. So simply, for example, you have any problem statement. Like you want to simulate this type of a plant, so that type of problem statement and that type of data you have to collect first. Then you feed the statistic related to that data, and you'll get the throughput. What will be the output of my factory that you'll able to get. Now, for example, I've taken this. Now, what I'll have to do, I have to give the connections to the factory to this model. So this part is going to go. It will go to the conveyor. So I have to select a connection. Here you can see an input and output role. This will send output to the machine. So I'll connect those everything at a faster rate. Instead of going to instead of explaining each and every stage, you'll get a direct idea. At the end, you'll have a ship. You are going to ship that model. Now I have to specify the status related to that model. Now this part is coming to the system for how much time? After each and every 5 minutes, the part is coming. What is the length of the conveyor? For example, I say 10 parts my conveyor can store and the index time of 1. What is the machine? This machine, for example, you can say this is a lathe operation. It will take 5 minutes. So I'm giving a timing of 5 minutes. Okay. You can select a various types of machine: batch, assembly, production, multiple cycle, multiple station. If you select a batch machine, you can combine a multiple number of part and you can do a batch operation there. So you say a production machine or assembly machine. So you can assemble a n number of quantity as per your requirement. So I say single and I say 5, cycle time of 5 machine. Then again, go to the conveyor. Similarly, 10, I'm saying length of the conveyor, it can store a 10 part at a time. But again, I go to the machine, it's say 5 minutes. Now I'm going to start a simulation directly. Very easily, I'm going to do a simulation here. All the statistics are given. Now slowly you will able to see each and every 5 minutes a part is coming and the part is going on the machine. Machine is working on that part as per the cycle time. Each and every machine is taking a 5 minutes. So we are doing a simulation using for example, I have taken a hypothetical problem here. I have taken a problem statement, for example, then I'm doing a simulation. I want to predict, for example, I want to see after 24 hours, how much production I'll get. I have given a timing of 1440 minutes, nothing but a 24 hour. And I'll increase the speed of the simulation. So it will give me the prediction. The timing is running at very faster rate. If I click on a batch run, I'll get a result at a very faster rate. For example, I'll click on a batch run directly. It will complete the calculation for a whole day. So 24 hours are completed. I go to the model. I check the statistics now. What is the statistics of that part? So you'll be able to see how many parts entered in my factory. 289 parts entered. Then it say 283 parts has been shipped. What is the average time required for each and every part? So their statistics and the results we'll able to get very easily in the simulation environment, and we can make some decision, what type of decision we want to make in the factory, as well as we can get the charts for that. So we get the charts for that factory also. Now I instead of going to the detail of this model, I'll just showcase you one ready-made model which I have built here. So here basically there is a raw material. It will go to the production machine. After production is done, it will go for the washing process. Why we are just given a name to this machine. Our area of focus is whole process. We are not focusing on an individual element, for example. So that is why we are going to focus on a whole process. The statistics related to that process is very much important. So there is a washing machine, then there is a weight counting machine, weighing, then there's a conveyor, and there is a packing. So there's a packing process is also going on. So this technician or labor, you can see it is helping a packing of that machine, packing process. And he also has given responsibility to repair a machine if it fails. So this washing machine, we have added a failure. We have added a breakdown. We have given a breakdown, and we have to predict what will be the throughput of my plant and what will be the improvement I can do. So we are given this machine can fail between uniform distribution, and we have given a triangular distribution for the repairing, and this labor is going to repair that machine. What I'm going to do, I'm going to start the simulation. As soon as this machine fails, you'll able to see this technician which is assisting a packing process. He will go and he'll repair this washing machine. So simulation has started. Now we'll able to see a failure. We'll also see a failure. You can see this failure has occurred. As I said, between 100 to 300 minutes, the failure will occur. This machine turned into red. Labor was doing a packing process. This labor now is repairing that machine. Because of that, all parts are getting bottleneck. I got a bottleneck in that area. He has repaired that. He gone to again his original work. Again, you will able to see this breakdown which we have added is a recurring breakdown. So depending on your requirement, you can add a breakdown, you can say a maintenance analysis, as well as, and then you will get the throughput, how much output I'm going to get. Now, for example, again, I'll wait for the one more breakdown. You can see this one more breakdown has occurred. Now I'll reduce the speed of the simulation. He is repairing that breakdown. In the meantime, you got a bottleneck there. There's a pileup of the parts in this buffer. This is buffer. He has repaired that machine. He again gone to his original position. Now what happened? For example, I want to see what is the results for 24 hours. So I'll increase. I'll run the model. I've given the timing of 24 hours. The simulation software will complete the results for the 24 hours. So 7 hours are completed. I'll click on the batch run. It will give me the results at a very faster rate. So now I've completed the simulation for 24 hours, and I check the statistics now. So I'll see here I got 289 parts, almost 290 parts entered in the system, but I got 254 parts throughput because 35 parts are in the work in progress. So now I want to make changes in my factory. So I can think 2-3 options. Instead of going to the actual changes in the shop floor, I can think 2-3 options, and I can get a simulation done here, and I'll able to get a prediction of that, which option will be better. So again, just note down this. I got how many parts? 289 parts entered, 250 parts, 254 parts I got out of the system. Now I'll reset that model. One thing a person can think, this technician, he gets busy with the packing as well as repairing. What will be the throughput I'll get if I add 2 technician? Okay, 254 parts we got previously. Now I have added what I've done technician 2. He will repair, he'll do the packing as well as one technician will do the repairing. Okay, so this one example we have done, and we are going to run the simulation for a batch run. I have done for 1 day. Now I'll check statistics now. Previously we were getting 254. Now I'm getting a 264. So this is a one option, like adding a one labor, I got hardly 10 parts more. Now what another action I'm going to change? Instead of adding a 2 labor, 2 technician, what I'll do, I will make a 1 technician only. This machine fails simultaneously, so I'll take one more machine to balance a line. For example, if one machine fails, another will work. Okay, so that is why I have added a 2 washing machine. Now technician is 1 only. With 1 machine, 1 labor, we got a 254 parts. With a 1 machine, 2 labors, we got a 264. Now I start a simulation with a 2 machine. Now you will able to see when 1 machine fail, this another machine will do the work of the failed machine. So you can see 1 machine is working. simultaneously this processing going on. Now what I'm going to do, I'll increase the speed of the simulation, run the batch run, and I see the statistics now. I'm able to see now. Previously, I was getting a 254. Then second simulation, I got a 264. Now I'm getting a 272. So this simulation software, this type of simulation trends help us to get what will be the best minimum resources I have to use to get the good throughput. Now you can even add the costing and all those things related to each and every part, as well as each and every machine. So you can get a costing analysis also. I'm not going to add that costing analysis right now. So you can think labor is suitable or adding a machine is suitable for long term. So these type of simulations will help you to get the prediction of your throughput of your factory. So each and every manufacturing industry uses this type of simulation tool. Nowadays, like you have a big basket or Grofers, so they use this type of simulation tool for the supply chain management also. So you'll able to see, if you visit LinkedIn, you'll able to see a lot of requirement of discrete event simulation software engineers. And now I'm going to move a readily available simulation model which I'm having with me. So this model you can see, it is basically a factory where there's an operation, lathe operation is going on in this environment. Then the production, the part which are produced here will be sent to the conveyor, and they will be processed here also. After that, there will be a carriers will come, basically gantry will come, they'll pick that parts and they will unload that in this area. So production is going on in this area, loading is going on in this area, it will be unloaded in that area. So real-time graphs and what is the situation, your plant is running, what environment, what are the utilization of the labor, what is the machine utilization, each and every statistics and real-time graphs we get in the virtual environment. So you can see there's a production is going on in that area. These are the carriers I come. Once the part comes here, they will pick that part and they will send that part to the unload station. What I'm going to do, I'm going to convert that model. This is a 2D model. Now we have a facility of a witness 3D, quick 3D. If I click here, this model will be converted into 3D environment, and you will be able to see the same model in the 3D environment. So it's converting into 3D. So a lot of industry as well as IITs, NITs using these type of simulation technologies for the manufacturing and production in the manufacturing production departments. So this model I have converted into 3D. So you build your model into 2D, it will give you the feel of a 3D in the 3D environment. So movement of the labor, they are moving from one station to another station. You can see the carriers are coming, they're picking the part, they're placing, they're unloading. So these type of simulation tools are very much used nowadays in the industry for the future prediction. So for the prediction of their throughput. Now when we say a modeling of a part, like we use a various type of simulation software like CATIA, Mastercam, or Pro Engineer, or a 3D software, or Siemens software, Solid Edge, Solid Cam. So those type of software we focus on a geometry level, a part level. Here we are focusing on an entire process. So what is the statistical related to that? Each and every thing, all statistics we able to get here and predict. We can predict our factory future. What will be the future of my factory? So these type of problem statement we can solve, and these type of tools are really used in the industry. This was not only a Ford. You see a Flex. Flextronics is basically like a electronic industry. We see a lot of models in the cell phone industry. Those get manufactured and assembled by this type of industry like Flextronics. So they also has like a industrial engineer requirement was there, and it was related to simulation. They wanted to workforce design. So basically what we are doing, we're doing a digital twin in the virtual environment. So of an entire site of that factory, and we do a simulation of that. They also use a witness simulation software and gather the simulation requirement and improvement of the business. So this type of digital twin in the format of a witness simulation software are very much useful to get the prediction of the future. Now not only this, we can also do a optimization. Now, for example, this was a plant, we have done the replica. Now I want to see what type of optimization I can do. Now, for example, this plant I have. Now I want to optimize this buffer. This buffer means basically an inventory storage area where I can store my inventory. So it has a capacity right now 90, for example. There is a conveyor. Conveyor has a capacity to store a 25 part, and there is one operator. Now I want to optimize in this plant. What is the optimum size my inventory storage should I have? What is the optimum size of my conveyor should I have? What is the optimum quantity of my operator should I have? So that optimization also we can do. We have to create a one model like this, for example. Then what we have to do? We have to, just a second. Okay, so basically what we are going to do, we are going to give the ranges to the inventory storage, to the conveyor, to the operator. We are going to use algorithm. We are going to use algorithm of a simulator analysis. And using that simulator analysis, we are going to predict what will the optimum resources you should have, get a maximum throughput. So that is what we are going to.
Mr. Suraj, you are left with another 3 minutes.
Yeah, so I'll complete this model after that. So you have this model. Then I go. What I'll do, instead of showing you to this, just a second. Okay, so I'll open that optimization window. Okay, so you got the optimization window here. So instead of creating that model with a different ranges, we are given a ranges in this environment only, and our objective is to maximize the throughput. And we are going to run that model for 10 days, for example, given your experience. So we run the simulation. What the simulation does, it will calculate the iterations using that we have used algorithm of adaptive thermostatic simulated analysis. We have a various other algorithm also, Six Sigma, or you have a mid max, you have a hill climb. So what this simulation software does, it will do a calculation of that plant, and it will give you what will be the maximum number of throughput. You will get a 2,730 parts if you have an inventory storage of 50, if you have a buffer to storage of a 20, operator quantity 1, and a conveyor length of 45. So it is calculating the simulation, and it will give you the best results in the background. So the simulation is calculation is going on. Let it be there. I'll discuss something other solution which we also have for the institute. Like we have a solution of a modular production system. Like we have a IoT based modular production system. You have a various stations here, and the stations are provided with the data collectors and the sensors. So you will get all the data and statistics will be collected here. That will be given to the console through IoT gateway. It will be given to the cloud, and you will able to get all the statistics in the IoT form, and you will able to get the results. So you will have a various station, like a feeder station, you have a processing station, sorting station, weighing station, so rotating station. So these stations and modular production system we have, and you will get the data points like this: sensor data, barcode data, number of job processed. So you will have a SCARA robot in that environment, or otherwise you want an AGV or industrial robot, 6-axis robot. So these type of stations we have, it's called as a modular production system. For the education institute, we provide this type of solution to get the insight of the modular production as well as the IoT with that. Then we have a FMS and SIM system also. So for example, if you have a factory and you want to build that factory, the digital twin also you want to build, and as well as you want to connect that factory with your simulation software, that is also possible, and you will get the real-time data of that factory and manufacturing environment in the simulation digital twin also. Digital twin simulation software we use, it's a visual components. It will have a various type of robots, CNC machines, gantry, lathes. So that type of machines we use that in the simulation software, and you'll able to get the results of that. We also have a robotic cells, 6-axis robotic cell, You'll have a Fanuc and Mitsubishi Robo, as well as you will get the connectivity for that, and you can get the IoT better experimentation in this environment, like how many operations done by robot, how many parts picked, those type of all the results you will get in the console, and you'll be able to control that. In the meantime, I'll check what results we got in the simulation environment. So till now, what is the best results I'll able to show you? 2,772 parts will get. You should have a buffer capacity 20, buffer 2 capacity 15, operator quantity 1, and conver length 40. So this is how we able to do a simulation. Still now, the best results is getting calculated by the simulator annealing algorithm. But I'll conclude my session here. I'll complete my session. Thank you very much for your time.
Thank you, Mr. Suraj.
Yes, sir.
Now we must thank Dr. Rameshwar Garu and Dr. Satyanarayan Garu for the excellent patience they have shown. They are there throughout the session. Now it is over to Dr. Satyanarayan Garu.
So thank you, Chair, convener of the program, Dr. Chandramohan Reddy. Presentations are really wonderful. You have touched upon various things, that right from connected factories and evaluation of the technologies, all these things. It has really given a very good insight for all the participants. Thank you very much. And also our Srini Perla has also given very good examples of how to apply these IoT technologies and then digital twins and all other, connected factories, all these things he has touched upon. And really it's, very, very, I think, a new technology we are all, witnessing right now. And coming to this, Mr. Soros, he has given also very good presentation on witness software, how to simulate the shop floor. Probably it is useful for the college, may not be useful for the industry. And modular production systems. In fact, no, these modular production systems are available in CITD. I have, for low-cost automation, that time, we have procured this from this German company. We have procured all these modular production systems. Probably, you can interact with the CITD also and see the physical systems available there. With this, now, I am giving back to our President, Dr. Rameswara, to request Mr. Anjaya to present the vote of thanks. Thank you very much.
Thank you very much, sir. Really, no words to say. This is a very excellent. Today, there is a workshop. Really, sir, it is. By heart, I'm congratulating to Chandramohan Reddy, sir. Really, very good. You have planned. All the speakers also very nice. Already our chairman has told that really no words. It is excellent, sir. Once again, we will conduct this type of programs in association with CBIT. Thanks to Satyanarayan sir for sharing this session. Now, I am requesting our Honored Secretary P. Anjaya, please propose the vote of thanks. Over to Anjaya, sir.
Sir, am I audible, sir? Hello?
You are audible, sir.
Sir. Respected Professor GPS Verma, Principal CBIT, and Dr. PVR Ravindra Reddy, Professor and HOD Mechanical Engineering Department, CBIT, Session Chairman, Dr. S. Satyanarayana, FIE, Immediate Past Chairman, IITSC, and speakers, Dr. Srini Perla, Global Head Technical Training, Sainant, Hyderabad, and Suraj Vaishnav, Dr. G. Chandramohan Reddy, FIE Professor, Mechanical Engineering Department, CBIT, former Principal, MGIT member, IITSC, and convener of the event. Our Chairman, Dr. G. Rameshwara Garu, IITSC, distinguished guest, fellow fraternity, participants from CBIT, ISKI, and participants from other various colleges, my friend K. N. Prakash Rao Garu from Vizag, and representatives of the media, ladies and gentlemen, good afternoon to all, sir. It gives me immense pleasure to perform the pleasant duty of proposing vote of thanks. On behalf of the Telangana State Center of II and on my own behalf, I convey our sincere and profound thanks to Dr. Srini Perla and Dr. G. Chandramohan Reddy, FIE, and Suraj Vaishnav for sharing their presentations. I convey thanks to Department of Mechanical Engineering, Chaitanya Bharati Institute of Technology for associating with us for conducting this program in a big way. I also convey our thanks to the dignitaries, committee members, corporate members, council members like G. Sudhakar and Brahma Reddy Garu and others, Ramna, Dr. Professor Ramna Bhanotu and K. Subbareddy Garu and C. Ramanujacharya Garu and other participants who have attended and made event successful. I thank the representative of the media and for their unstinted support to cover the proceedings of the event. Thanks, one and all, sir.
Thank you, Anjay. Thank you very much. Thanks to all, sir. Now we are closing the